this next segment in the series is going to focus on the commercial, mechanical, and lighting. Now, with that being said, this is only a 4-hour training session. And when we start talking about 403 of the Energy Code, the mechanical section, it's rather extensive. And quite honestly, I do an 8-hour class on it and still can't touch on every single aspect of it. So just so that we are aware, today's class is focusing on some of the more probably utilized sections for commercial mechanical, not every opportunity with it. But with that being said, let's go ahead and take a look at things. So, just as a friendly reminder, when it comes to the Energy Code, when is a project considered to be commercial? I stumped you in the first few minutes. Wow. There we go. Okay. So, to figure out commercial, we actually have to look at the definition of what a residential structure is. So per the Energy Code and the Energy Code alone, it considers a residential building to be those single-family, two-family, townhouses, but it also includes R2s, R3s, and R4s that are 3 stories or less above grade plane. So that means potentially you have projects, whoops, wrong way. And then for commercial, anything that doesn't fall under the residential definition is considered commercial. So you could have a project that builds out of the IECC because it's commercial, and then turn around and have to design out of the residential side of the Energy Code. So they're kicked to the back of the book. Mixed use. Mixed use becomes fun, especially when you start talking about things like everybody thinks about it. It's really difficult if you're a mixed use building, if you're going to do the thermal envelope. And in my opinion, mixed use buildings for the thermal envelope, that's the easiest part of trying to figure it out. Trying to figure out mixed use buildings for mechanical, in my opinion, is incredibly difficult because the code says you're going to follow the provisions out of the commercial side of the code for what's going to be considered commercial, and then follow the residential provisions for the portions of the structure that are considered to be residential. So if you have a 3-story building, bottom floor is commercial and the top 2 floors are residential. If it's a single mechanical system, which side of the book do you look at? Commercial. Do you know why? I wouldn't, they're kind of comparable, but the reason why is because on the residential side of the Energy Code, it kicks you to the commercial side. It says if you have a system that's doing multiple units, it sends you over to 403 for that. But you are absolutely on the right track on it. So isn't that, see, didn't we already start off with a lot of fun there? All right. So one of the very, very first sections of the code talks about heating and cooling load calculations, that you must have heating and cooling load calculations performed to the standard of ASHRAE 183, and then you're going to use that information to do things like size your mechanical systems. So, when we talk about heating and cooling load calculations, does everybody know what's involved in those calculations? Somebody shake their head no, otherwise this next slide will, okay, thank you. All right, let's talk about some of the aspects that go into the heating and cooling load calculations. Ooh, really quickly, can anybody tell me, while the energy code does require heating and cooling load calculations, what other code requires heating and cooling load calculations? Section 312 of the mechanical code also requires heating and cooling load calculations. For the longest time, when I would write up a review comment and I'd put this section down saying that the energy code requires it, I would get pushback after pushback after pushback after pushback. Once I started having this one and tying it to the mechanical code, nobody argued with me after that. Which shouldn't be the situation, right? The energy code, the mechanical code, the plumbing code, all of those codes are there to instill the safety, welfare, and health of the occupants of that building. Anybody have any questions walking into this building as to whether it was safe? Nobody? Anybody wonder whether you were going to be warm or if you needed to bring jackets in here? I mean, I know we have jackets, but it's cold outside. It's not cold in here, right? So part of that is because we paid attention to things like this. All right. So what goes into it? Well, we've got elevation, our heating and cooling degree days, how much glazing that project has, because just like when you're doing a residential heating cooling load calculation, a manual J, there are two aspects that have a big impact on your heating and cooling loads: glazing, roof or ceiling, right? So same here, the amount of glazing, what direction it is, do we have any shading going on? What's the solar heat gain coefficient? Overhangs, then of course our thermal envelope that extends to insulation, because that's important to know. Roofing material, is it light, is it dark, is it reflective, all that fun stuff. How many lights you have, the kind of lights you have, and then the occupant load. So just kind of running through it really quickly here. There's typically two software reports that we get for heating and cooling load calcs. We either get HAP Carrier or we get Train Trace. What do you guys typically seeing? Or you have no idea, you're just happy you got heating and cooling load calculations and don't pay attention to what software provided it. Anyone? All right. So for this particular one, if we were looking for the elevation, we would look here. This says Denver, Colorado. That lets us know that when they put it in, that was taken into account. Our heating and cooling load degree days. This building's going to be open from January to December. Seems appropriate. If it happens to be a seasonal building, right, it's only open from May to September, then right here we should be seeing May to September. And then the amount of glazing. This is the second page of the report. You can see all the windows, the information there. This calculation of the BTUs for your sensible and latent loads, we're looking at sensible loads right now, but it took into account the amount of glazing, the direction, type of glazing, solar heat gain coefficient, and overhangs. So how many of you are plans examiners? How many of you are mechanical engineers, inspectors, contractors? Who did I miss? Architects, sorry, the architects? Oh, permit tech. The most important position in a building department. Lots of people think it's the building official. Nope, it's the permit tech. So the reason why this is so gratefully important, but yet when you look at the numbers there, can you guys see those numbers and know exactly what the input was to ensure that we have a correct heating and cooling load calculations? How many of you see those numbers and say, I know what they put in? Anyone? Anybody know how to verify that? So, when you're doing a heating and cooling load calculation for both reports, there's a portion of the report that may be provided to you that you probably have overlooked 1,000 times, or it's not being provided to you, is there's a section that talks about, and it's this nice little piece in there. One, it puts in there, here's the windows, this is the U factor for it, the solar heat gain coefficient for it, and the direction that it's facing. So if you look at that part of the report and those values match what's in the plans, then you know that those values that are listed up there are pretty well trusted. And our insulation values and roofing material, all of that's in there. Again, when we talk about insulation values in that same part of the report, it actually has a breakdown of what they put in for their wall assemblies. Now, when I talk about a breakdown, they're not just inputting things like the wall's going to have an R20 cavity insulation. They literally do a wall assembly. So you'll see it's going to say 1/2-inch gyp. It's going to say it's using 2x6 studs. They put in an R20 in the cavity. It's having this type of sheathing. If there's an air gap, if there's whatever their exterior cladding is, it breaks that wall assembly down. So whatever that wall assembly that they provide you should also match what you get on the plans. How many of you are like, I don't have to sit here for the rest of the class because I've learned my one new thing for the day? And you're like, well, I drove all the way here. I'll listen to her. All right, and then lighting. Lighting used to be like one of the biggest impacts on your heating and cooling loads. But since the lighting industry and manufacturing took hold of the energy code, it still has an impact, don't get me wrong, but it's not quite as bad as it used to be, but we still want that information. And then our occupant load. How many people are they saying are going to be in that building? That's important. So if I look at my occupant load and it says 120 and they have in there 270, that's a little bit of a problem there. How many of you have ever looked at the number of people in a heating and cooling load calculation? Yeah. All right, and then that brings us to the fun part down here, which gives us our cooling load and our heating loads. We get to take that and apply it to the mechanical equipment. It really should be an appliance because they're an appliance, not an equipment. Schedule and verify that these loads don't exceed the loads that are here. Now, here's the other thing. When you're looking at this schedule, don't ever look at the input. That's not what we're trying to verify. We're always trying to verify the output matches the cooling loads. And just so that I could give you a preview of the next slide, you'll notice output is blue and has been put into the code to ensure that everybody is on the same page, right? Because the output capacity, is dependent on a few things. The efficiency, it takes into account, elevation and all that fun stuff. So a piece of equipment that is going to work here is probably not going to have the same output that would have, in like Bemidji Minnesota that's at 600 feet above sea level, right? We're slightly higher than them. All right, sizing. Sizing is so incredibly important with the equipment. It used to be that a lot of times, because the mechanical section of the energy code, people will do their due diligence, right? They'll go to 401, 402. They kind of skip 403 because it's somewhat difficult to understand. They'll go to 404, 405, do all that. But 403 is just one of those sections that wasn't maybe the most paid attention to. But one thing that was paid attention to is they're like, well, we're going to make sure that we size the equipment appropriately. And so this section is valuable because it's a section that I think was probably utilized the most. Now, this is what I like. So it says if a single piece of equipment is doing both heating and cooling, then the equipment has to meet either the heating or cooling loads, and the other being the smallest one possible. So if you had a single piece of equipment that was going to handle one, it would have to handle one of these two loads. And then if you were doing heating, because it's probably more important to size the heating up here than cooling, then for your cooling numbers, you would just want to ensure that it's as close as possible. So they're not saying if it's one piece of equipment, you have to figure out a piece of equipment that meets both of them. They're saying pick one and then make the other one as close as possible. I like that one. I also like this because it used to say it had to match exactly. And how often do you find a piece of cooling equipment that's 513,863? Not often. You might find, 550. And per the code, way back when, not that far ago, that didn't comply with the code. Everybody just went to the next available size because common sense. Now let's talk about exceptions here. If you happen to have a system, right, that has multiple pieces of equipment to it, kind of indicating here's my main system, here's my backup. Particularly, you find that a lot in like computer rooms, data centers, something of that nature. And so you need that backup piece of equipment, or hospitals, if that original piece of equipment fails. So what there is in here is basically saying there just has to be controls involved. So you should be getting like sequence of operations that states this backup system only kicks on when the first system fails, malfunctions, or isn't able to do it for whatever reason. And typically, like I said, I see that a lot in like computer rooms, big computer rooms, data centers, hospitals, things of that nature. All right, now that we've sized the equipment, we want to ensure that that mechanical equipment has the correct efficiency to it. Now these tables are updated, every cycle. The latest and greatest federal minimum standard gets placed into the code. But just so you know, there are now 16 tables in there. How many of you have had lots of fun going into all of these tables and trying to figure out if the efficiency that's being proposed is the correct efficiency? Anybody have fun with that? Oh yeah, okay. Now when I say have fun with that, is it have fun like, oh my gosh, I don't know which table I'm supposed to be looking into and then which category does it fill in? Or is it truly, I have fun doing this?
Pretty easy to Usually it's gas boilers that I'm looking at, so.
Oh, well then, yeah, that does make it easy. But a lot of times, you know, there's a lot involved with it, and trying to navigate those tables. I can't tell you how many times I have heard about I don't know which row or which table I'm supposed to look in. And a great tool that I utilize and I advocate on is getting a mechanical comm check, because that mechanical comm check does a lot more than many people realize, I think. And so it provides us with the efficiencies on there, what they're proposing their efficiency is, what it actually is, and then you can take that, look at the plans, and make sure that the appliance schedule matches what's being stated there. And which is helpful, because then when the whole project gets to be out in the field, it's easier to kind of follow and ensure that we have everything that we need. All right, economizers. How many of you are seeing a lot of economizers with the project? So economizers are only required if they utilize the prescriptive path. So if they chose for their energy compliance path to go with the total building performance, they don't have to install an economizer. That doesn't mean that they won't, but it's not a code requirement. This section only applies if the project chooses to utilize any one of the options of the prescriptive path. They will have to utilize an economizer. And an economizer is basically a big giant damper that opens up when the air outside is cooler than the demand for air inside. So basically it opens up, lets the outside come in and precondition things, and help with the amount of energy that's actually being utilized. Now, there are some exceptions for having an economizer. So if you fall under any one of these and you can demonstrate it, then you don't have to install an economizer in your system. I would say probably 10 years ago, economizers were, bless you, like almost a 4-letter word, like, oh, no, we'll find any reason to not have an economizer. And I think an understanding of the economizer, and now the economizer is like, oh yeah, you can come along, you can play in the sandbox with us, we'll allow you to hang out with the cool kids. All right, so let's talk a little bit about what these economizers actually have to do. So you'll notice, all throughout I have bullet points kind of breaking it out, because if you look at the language that's in 403, while it's not completely in engineerese, it's a dialect of engineerese that's kind of a cross between, English and engineerese, or code language and engineerese. So I have it broken out into bullet points to hopefully make it a little bit easier to digest the information that there is. So the economizer is going to be integrated with the cooling system, which makes sense, right? And then the idea is that the economizer works on its own, and the cooling system isn't in operation when the economizer is functioning the way that it should be. Now, it does require that you do not oversize the supply fan for that economizer load. And so there's also a chart that you're going to utilize if it happens to be a 2-stage system. Now, when we talk about the economizer, this one basically is saying that you've got to have controls so that it doesn't operate at the same time. It's very similar to what you see here where it says it can't operate at the same time. This goes on there, and then it also has an exception in there, and that exception is for the variable air volume systems. It can't, the zone level heating to increase because of a reduction of the supply air temperature. So they're making sure that, how do I want to put this? They're trying to ensure that those VAV systems that we're working together and they're not combating each other. Now, when we talk about an economizer heating system impact on there, part of what this section is really trying to ensure is that we have some controls, and these controls are really trying to navigate so that when the outside is too cold, that the air being brought in doesn't trigger the heating system to come on, because that kind of defeats the whole purpose of why we have it, right? Is free air conditioning, but not to the point that it makes it so. Let's just pretend that we're a gym, right? So the gym is probably a little warm. Well, it's 2 below 0 outside. You might have a little bit of air come in, but you aren't going to have air come in that lowers the heat in here to the point of where now the heat's going to come on. So the idea is, you know, it's there, it's used, but not at the expense of triggering more energy usage, right? All right, so then the question becomes, how do you see that information on a set of plans or when you're out in the field? One of your best friends, I have mechanical engineers that are absolutely wonderful, and everyone's like, oh my gosh, I have 20 pages for this mechanical system. And you got your duct design, you have your layout for your floor plan, maybe you have 5 of those, you have a equipment schedule, right? And then the rest of the pages are actually sequence of operations. And that is how we get a lot of that information. Sometimes I get a note in the schedule that says, hey, I have an economizer, and then they have like 5 notes that talk about the economizer. The economizer will not trigger the heating system, like kind of regurgitates a little bit of what we're talking about today, but typically I see a lot in a sequence of operation. All right, design capacity. For that one, you're going to modulate outdoor air and return air for 100% of the design supply air, with outdoor air for cooling. And then the signal breakdown is basically the dampers have to be sequenced with what the cooling equipment is doing, and not controlled only by mixed air temperatures unless it pertains to a certain situation. And an example of that would be that single zone system. Oops. All right, high limit shut off. So it has to be capable of automatically reducing that outdoor air intake when it's no longer needed to cool down the building. This kind of seems like, duh, doesn't some of the previous sections kind of mention that, but it's in there. It also has to have a high limit controls for the climate zone in accordance with the table, and I think, did I not put the table in here? I didn't put the table in here. That's not the right one. There we go. So it would have to be in accordance with the table. Now, relief of excess air. So the idea is we want to ensure that we're providing all of this, but we also want to ensure that we are not over pressurizing, the building while this is happening. So what you're going to do is there's going to be something in here, and typically, again, I see it as a sequence of operation or a note that's provided saying the system will ensure that the pressurizing of the building does not exceed while the economizer is in use or will shut down. I've seen a lot of things of that nature, but typically when I want to see a set of plans, and when it comes to an economizer, I do want more information than, great, we have an economizer. Wonderful. I'm very happy that we have an economizer on the system, but I want to ensure that I have all the various controls. We don't overpressurize. We have it the fan sized appropriately. Now, I'm not going to ask for, calculations necessarily. Show me that it meets that, because we'll take care of that in a minute. But I do want these types of information going to be placed and be available so that I can look at it and understand, sorry, Adam, that we're meeting the intent of it. Because let's face it, where do we get our tangible energy efficiency out of the energy code? It's our utility bills. What's a big impact of our utility bills? Our heating and cooling equipment, right? So this is incredibly important. Do we have to have a strong thermal envelope to make this all work? Absolutely. And I'm not saying ignore the thermal envelope, but the mechanical systems actually has a really big impact, and it has a big enough impact that that's what everybody latches onto as to determining, is this a measure of energy efficiency that should be put in the code, right? What's the return on investment for it? They look at utility for that. So keep that in mind. This section of the code, C403, everybody should get more familiarized with it to, get comfortable with it. Doesn't mean you take everything out of C403 and plop it in and try to do it. I like to think of, let's take little steps. Oh, great, I have an economizer. How can I show this on the plan so the plans examiner knows what I'm trying to do, and so that we get it out in the field, right? It's little steps for all that. All right, we got to have dampers for our return and exhaust return, and outdoor dampers for economizers. Those dampers also have to comply with section C403.7.7. Anybody know what that section is referring to? Who's going to get a gold star for it? I see code books. You could look it up. I'll give you a second. So what's required of dampers on the commercial code? Dampers are required to be motorized. So section C403.7.7 is actually a section that governs how you're going to treat dampers. It says they have to be motorized, they have to meet all this various criteria, and then there are some exceptions involved with it. So in the thermal envelope section, right, our intakes, our exhausts, our elevators, all of that, there's a section in there that says, hey, you got to put dampers on here, and you have to comply with C403.7.7. So there's several markers that throw you to that section to ensure that we're paying attention to it, because we just made a building really tight with air barriers, with insulation, with good windows, non-leaky windows, sealing everything up, right? And then we put a big giant hole in it for good reason, right? Intake, exhaust. So now they're like, okay, not only are we going to tell you out of the thermal envelope to do dampers, we're also ensuring in the mechanical code that we start sending you to that section. All right. So that was all dealing with economizers. Let's talk about our water side economizers. So we got two, right? Air economizers, water side economizers. So if you have a water size economizer, the system has to be designed for a load at a temperature of 50 degrees at dry bulb and 45 degrees for wet bulb. That's what the code requires. Now, there are two exceptions. Those two exceptions pertain to computer rooms and data centers. Computer rooms and data centers are a whole nother ball of wax when it comes to the energy code. In fact, if you go into section C403.1, it's like in the first section there. It specifically calls out things that, parts of the code that they have to comply with out of C403. Not only does it state that you have to comply with these sections out of C403, it then throws you over into a whole other standard, 90.4, to deal with a lot of the components of it. But in this particular instance, it's not a separate section, it just has an exception for it. And then exception 3 is for buildings that happen to have an excessive indoor moisture, so swimming pool areas, right? Gym, something of that nature, right? Potentially. Then the cooling coil may not be cold enough to condense that moisture in the supply air, so then the design conditions are dropped for that out of this particular section. Now, there are two options that are going to limit the amount of energy loss that happens when there's a pressure drop across the pre-cooling coils. The first limit is for when you have less than 15 feet of water for pressure drop. The second one is dealing when you have more than that 15 feet of water and you're only circulating through the device when the economizer happens to be on. So, question for you. How many of you in projects, whether you're designing them, part of the team, plans examiners, inspectors, contractors, how many of you are seeing and utilizing air economizers for the most part? How many of you are seeing water side economizers for the most part? How many of you are not sure because you saw the word economizer and thought, we are good? And remember, safe space, it's all good, right? All right. Now that we have an economizer, guess what? There's a requirement that the economizer has to have a fault and detection diagnostics to it. Now, what I will say for this has been in the code for a few cycles. There was always this concern, this add costs, all the fun things that are talked about. Most economizers are built with this system kind of in the I don't want to say problem, or the roadblock to it is it'll communicate and it'll let you know all this stuff. The problem is nobody wants to talk to it. There's nobody on the other end for the economizer or the fault detection diagnostics to say, hey, I'm not working well. I'm having a bad day. Can you please, help me out? And so now there's more and more systems that are connecting so that these are not really as hurdly, because Hope's creating new words today, than they have been in the past. But the code does have criteria as far as what are these systems actually paying attention to. So here is the first slide of many to talk about the things that it needs to address. So there has to be sensors that are going to monitor the outdoor air, the supply air, and the return air. There has to be temperature sensors They also have to be accurate within 2 degrees, right? Plus or minus 2 degrees. And they have to have a range of the 40 degrees all the way to 80 degrees. Now, there has to be a refrigerant pressure sensor when it's used, and this one has to have an accuracy of 3% of that full scale. Now, the out unit controller also has to be configured to provide a status for these 6 items. Free cooling is available. The economizer happens to be enabled. A compressor is enabled. The heating is enabled. Mixed air, low limit, cycle active, and the current value of each sensor. So with looking at this and some of the things that I talked about earlier, can you see why these 6 items were picked to ensure that they're monitoring? If I were to, I don't want to pick this up because I'm afraid it's going to shut everything down, but if I picked up my iPad, right? I'm the building whatever, maintenance, building owner, guy in charge, woman in charge, whomever. I pick it up and I look and it tells me, okay, I can have free cooling? Absolutely, that's where we're at. But why do I have free cooling and the economizer's enabled and the heating's enabled? That lets me know, ooh, I need to maybe look a little bit further into my system as to what's going on with it. Which brings me to this one. It says that the whatever controller, right, whatever it's going to be. Nowadays, it's probably this iPad type of deal, or it could be hooked up to many other things. But it has to have the capacity and the capability to be able to manually initiate the operations that we see coming on here, right? That it will allow for the compressor, the economizers, fans, heating system, that it initiates it, and it also can be tested and verified at any point, right? It also has to be configured to report faults to a fault management system, whatever that's going to be, right? Whatever it wants to let us know it's having a bad day, and can we give it a hug to make it feel better, right? All right, so the fault and diagnostic system, it has to be able to detect when these faults are active. So if the air temperature sensor happens to fail or is in failure now, it needs to let us know that, hey, something's going on there. Or that the economizer is supposed to be working and it happens to not be functioning the way that it needs to be functioning. It also lets us know if the damper's not operating correctly, right? It's not modulating as it should. Should it be fully open? Should it be partially open? Whatever the case may be. It also lets us know that we happen to have excess outdoor air and we are overpressurizing this building. So these are the faults that it should demonstrate. So with all of this criteria that's in there, how many of you are seeing this information on the plans? Whether you're out in the field, in the office, or putting it on the plans themselves. Anybody? You might see it, I'll let you know, I don't typically see it as a sequence of operation. Where I may find this information, if it's provided, is in a spec book. And honestly, I'm okay with that. The spec book has its place, right? And I think this information saying, hey, I have a economizer, it's an air side economizer, it has all these things, it's going to meet the criteria of XYZ found in spec book. The controls, will be found in spec book. All right, we're good. Our fault detection diagnostic is going to be in that spec book. But as I mentioned before, there is a lovely, lovely tool out there that is incredibly helpful with a lot of what we just talked about. And that happens to be the mechanical ComCheck compliance certificate. Unless they're going with the total building performance pathway, which they then have to provide a lot of this information, and it actually has to be placed. It has its own criteria of where it has to be placed on the plans. But if we're going prescriptive, this report for me is absolutely invaluable. And whenever I'm talking to people about mechanical, I like to say, you know what? There's probably somebody in here who is a mechanical engineer. I know I'm not a mechanical engineer, but this report helps me feel like a mechanical engineer. Just kidding. But it does provide a lot of information for us. So if we took this and we looked at right here, it gives us what type of heating equipment are they going to use? What type of an appliance? It's a central furnace. Wonderful. I can then take that and match it to the plans. Are they putting that on the plans? Fuel source. It's gas. All right. Also helpful to know. Now, in this particular one, it has capacity unknown. This should have been kicked back because we need to know what that capacity is, right? But I like to have it because I think it's a good one to show, saying, hey, by the way, don't forget. It also tells us what they're proposing their efficiency for their equipment is and what is required for there. So in that particular instance, it's wonderful. How many of you have looked at these and thought, we are good to go with that information? How many of you have ever had question about whether the efficiency was right? Because if you think about it, probably more on the, well, it would be on the cooling side, right? It'll say it has a 13 EER. And then it says, as it's proposed, and then it says for the required, it's a 14 IEER. And you're like, how do I know whether they're comparable? Well, the good news is ComCheck knows. And if it doesn't work, it puts a note on the report that tells you it does not meet the efficiency. So this report really does help you in that aspect. So now if we looked at our cooling, oh, that went to the wrong one. Our cooling should have been down here. Oh, there it goes. Okay. Well, Hope's eyes must have been tired when she put this together. Our capacity, again, it's still unknown. But this one gives us our efficiency. It gives us our proposed efficiency, which is 13.4 and SEER 2. Everybody understand the difference between SEER and SEER 2? Anybody? Okay. So SEER was the original efficiency, because there's a whole bunch of different efficiencies, right? We got SEER, EER, I didn't put those in there, I probably should have, that, you know, different types of efficiency for different types of equipment. Now, what happened is 21, 22, I can't remember exactly, there was a new federal requirement that stated mechanical equipment had to utilize a newer standard. So in 2023, the pieces of equipment had new standards that they had to utilize. So to differentiate between the old stuff and the new stuff, the old stuff is SEER, the new stuff is SEER 2. Now, with that being said, last year, kicked in because we are considered the north by the federal map of things. And so because of that, we were still allowed to utilize and install the SEER 1s. Now it's come to we're installing SEER 2s because everybody's pretty much on that SEER 2 situation, or IEER 2 or COP 2. And you'll notice if you go look at the tables, it has a delineation in there. It'll say before January 1st of 2023, you're this. And then after January 1st, you're a different number, and it usually will have like a SEER 2. Sometimes it'll still say SEER 1, depending on the type of equipment, but the efficiency's all changed. All right, and you'll also note that for some equipment, this says proposed efficiency, this says required efficiency. This also has a partial part load efficiency and required part load efficiency. So there are some pieces of equipment out there. Don't ask me which ones, because for the life of me, I can't remember it right off the top of my head. But there are some requirements that revolve around the part load. But ComCheck will take that into account for it. Anything that we see that is missing? If I pull this out. Fuel source, it does show it here as gas. For cooling, it doesn't show it there. It didn't give us the economizer info, but it does have the capability of providing that for us. So when we talk about the economizer, it would be over here on the right-hand side, off of that first row of the cooling. This one happens to say an air economizer. Now, it's not saying that it meets all the criteria we just talked about out of the code. What it is telling you is in that design, they included an air economizer, and we know now to go look at that stuff to ensure that it's there. Oh, it didn't make it in here. I have one in there too that actually says economizer not provided or something of that nature, and then it says exception. For it to not be installed, you have to, when you're in ComCheck in the software, you actually have to go through and click which exception you are utilizing. And then you, as everybody looking at the project afterwards, would just ensure, oh yeah, we meet it. We're only, this size, so we don't need to have an economizer. Let's just go ahead and dive into it. This really is dealing with the design of the fan system. Now, it only kicks in if you happen to have a single fan that exceeds 5 horsepower, or you have multiple fans in a system that equates to that 5 horsepower. I should say exceeds that 5 horsepower to it. Anybody see on plans, and like in the schedule, it'll say 3 horsepower or what have you, and you thought, why are they putting that in there? Well, they're putting that in there because they're trying to demonstrate, hey, we don't have to comply with this section, right? I can just say we have 3 horsepower, call it good, and move on with life. Now, for this requirement, it gives you 2 options on how you're going to design this system to meet the criteria. You can either do the nameplate motor, I always say that wrong, motor horsepower, which is probably the more simplified option in all of it, or you can utilize the brake horsepower option with that one. That one has multiple components that are with it, so it's not exactly as straightforward as option 1. The other thing is, whatever you do, you cannot exceed the values when the calculations are done when it comes to table C403.8.1 parentheses 1. And that table is going to apply to whichever option you choose to design this system to. Now, there is a little component in there, and they do pull out VAV systems in several parts of these sections where you're going to treat them slightly different just because they kind of work a little bit differently. But the other thing is we also have some exceptions going on here. So one of the exceptions is if you happen to be a hospital, a laboratory, and I am not going to say this word right, vivarium. If you're one of those, then you happen to be exempt. Or if you have individual exhaust fans that are 1 horsepower or less, then this is not going to apply to it. How many of you have ever gotten the calculations for the plans examiners that involve with 403.8.1? Anyone? Or maybe anybody seen this information provided on the plans for you? Okay. How many of you look at mechanical comm checks? Anyone? You guys, I'm trying to keep you from the gym tonight. If you raise your hand, then you don't have to go to the gym tonight. So, okay. We'll just keep that in mind here as we move forward. This is the fun table. Now, when you look at this table, if you had something that said, I don't know, 8 horsepowers, would you be able to figure out with what is provided on the plans in here to determine, does it meet this criteria? Did this table just make you realize or feel like, oh my gosh, I am so out of my element? Anybody feel out of their element right now? Okay, safe space. This, in my opinion, this is probably one of the most engineerese written couple of sections that come in here. And then tables. How many of you like math? Okay, I have a couple of people that raise their hands. How many of you don't like math? Raise your hand. I happen to be the latter. I'm not a math person. I'll do math, but this math, I don't necessarily want to do, right? Because it's not even that straightforward, right? You got your brake horsepower to your CFMs time 0.000494 plus A. What's A? Anybody know what the A is? Yes. Divided by 4131. So who raised their hand that they liked math? Is your hand still up saying, I think this would be fun?
They give you the equation, they give you the variables, and you just put it that.
All right, well, everybody knows now who to send this to. Hey, can you verify their work? All right, so we have this lovely table. As you mentioned, we have all the lovely variables here, and they are spelled out. You always get a nice little explanation when we have equations, right? In the code book, we have equation 4.2. Well, if you see equation 4-2, it says A divided by B multiplied by C multiplied by D. And then it says A is X, B is C, you know, anyway. So it does explain it for us. All right. Now let us talk about the motor nameplate horsepower with this. This really is trying to limit the size of the fan that's going to be selected for the system. It is required for the brake horsepower to actually be stated on the plans. If we go into C103.2, C103.2 is the section of the code that says all this information is required to be placed on those rolled up construction documents. Your fan horsepower and your fan system information is in that list. Not only is it in that list, it then goes into this section and says, oh yeah, by the way, just in case you don't look at C103.2, I'm also going to tell you, you're going to have to give me that information on those plans. Now, the idea of this concept and what we were just talking about is, again, we're trying to ensure that we are not oversizing the fan system for the mechanical system there. So basically, we're trying to ensure we're not oversizing. And if what it does say when you do all this stuff, that again, they don't want you to undersize it either. They're saying, okay, go to the next available size of it, right? So this, in my opinion, that part that was put in there is the common sense component with all of it. So I can't use that arm. So in this, when it talks about oversizing and all of that, so it says when fans are less than the 6 horsepower, then you have 1.5 fan brake horsepower. And for fans that happen to be greater than the 6, now you have a 1.3 brake horsepower. Now, in this particular section, it does exempt if you have variable frequency drives, and if you happen to have fans that have an input that's less than the 0.89 kilowatts are also exempt from all of this. Now, in this particular section, it also says fans complying with C403.8.1 is exempt. When you're utilizing option 1, this is our option 1. Whoop. This is our option 2. So in this instance, so if you go with 1, you don't have to comply with this one. So it's incredibly important to know which option they utilized, because are they taking into account the fan brake horsepower and all of this? Do you have to worry about how much electrical input there is? At this point, if they're utilizing 1, you get to skip this section altogether. And then if you happen to have a fan that's their nameplate horsepower is less than 1, then they happen to be exempt. Now, we can't just have fans for the sake of fans. We also have to ensure that they happen to be efficient, energy efficient fans. So there is a fan energy index that's part of all of this. So what a fan energy index is there's a definition there, and it's the ratio of the electric input power of a reference fan to the input power of the actual fan as calculated when you're doing AMCA 208. Now, depending on the fan and for the system that it is, basically if you have a fan or a multitude of fans, you have to demonstrate that you have a fan energy index of at least 1, unless you have to be part of a variable air volume system. Then you only have to have a 0.95 fan energy index value to it. Has any of you seen where on the plans, typically I see it in the schedules, that states my fan energy index is XYZ? Okay? Are you guys ready to have your brains explode yet? All right, let's talk about the exceptions here. So, This is the exceptions for when you do not have to have a fan energy index for it. So the first one is if they are not embedded fans with motor nameplate horsepower that's less than 1 horsepower, or with a nameplate electrical that is less than the 0.89. Number 2 is embedded fans with a motor nameplate horsepower of 5 or less, with a fan system electrical input power of 4.1 kilowatts or less. Multiple fans operating in a series or parallel. If the functional equivalent of the single fan, it has a combined motor nameplate horsepower of 5 or less with a fan electrical input power of 4.1 kilowatts or less. 4 is if they happen to be part of an equipment covered in section 403.3.2. Fans included in an equipment package certified by an approved agency for air or energy performance. Ceiling fans, this is a good one. Ceiling fans, which are defined as non-portable devices suspended from a ceiling or overhead structure for circulating air via the rotation of the blades. I think that one's a good one to have in there. Fans used for moving gases at temperatures above 482 degrees. Fans used for operation in explosive atmospheres. That's probably a good one too. Reversible fans used for tunnel ventilations. Fans that are intended to operate during emergency conditions. It doesn't specify what those emergency conditions are, which is good, because otherwise, if you had a list, inadvertently, you're always going to leave something off, right? And it is an emergency. And then anything that happens to be outside of the scope of AMCA 280. So with that being said, where might you find all of this information when it comes to the fans? Anybody seeing this information being placed on the plans? Anybody? Well, typically you wouldn't see it in a spec book, but doesn't mean that there wouldn't be a project that would put this information in a spec book. Anybody have any ideas of where you might find this information? Should be on the appliance schedule, absolutely. It could have that information in there, and I have seen in the schedule where sometimes sometimes they'll have a fan schedule, or sometimes in their system, it might say utilizing fan system 3 or something, and then there would be a separate table, and it would say fan system 3 consists of 5 fans at 4.2 horsepower or whatever, I don't know. I'm trying to make it up. And then it'll say, note ABC, and then note ABC actually gives us, and it'll say, I'm using option 1. They don't typically say option 1, horsepower. It just tells me option 1 or option 2. But one of the most useful tools that is there happens to be ComCheck. The mechanical ComCheck actually provides that information there for you. So in this document, you could have one document that even if you are just starting off trying to figure out the mechanical stuff, you have a document that just knocked out, 4 different sections out of the code? So, I forgot if this works on there. Oh, it does. Okay, great. So in this, it's telling us Our fan system 1, it tells us which option they're doing. It says motor nameplate horsepower method. Anybody know which option that was? Was that 1 or 2? Bless you, by the way. 1, correct. So they're using option 1, the more simplified option in all of this. Now, the great thing about this and why I love it so much is it tells you with the design of what it is, whether it passes or not. So right here it tells me, okay, with what they inputted into the system, it passes. It also has what our volume is, right? Because remember there was that first table I showed you for all that fun stuff? It shows me the nameplate horsepower of the fan. So it says it's 5. It also shows me the efficiency of the fan. It's 5. What was the minimum that it had to be? 1. It had to have a fan efficiency index of at least 1. So this one is 5, unless it's VAV, and then it's a 0.95. But this one meets it because we're at 5. Now here's the fun thing. I don't remember if I put the slide in here or not, but in this particular instance, I've had people say, well, how can I trust that this is correct? Because if you go in and you get a report that fails, there's a note on there. 1, it says fails here. And then there's a note in there that says it fails because fan efficiency doesn't meet it, or it exceeds, or it doesn't. It provides you the reason why it doesn't fail or why it doesn't pass. So in my mind, it is a wonderful tool, especially as we are starting off in, like gaining compliance with the mechanical section of the code, no matter where you are in the process. So now this system says I have a fan system and it's unspecified. It should give us the information on there. Why might it not have the information going on and the fan system would be considered unspecified? Could be a hospital, meaning it met one of the plethora of exceptions for it. It doesn't say in there like I'm using exception A, right? But it will say unspecified. And you could, at this point, if it was a hospital, you received this, it said unspecified, you'd be like, well, it's a hospital. I know that it's one of the exceptions out of the section, so I don't have to worry about it and I can move on with life. But if it's something else, and it should have it, it should tell us all this information on there. So if it said unspecified, it could be a matter of a simple thing. Like in the software itself, if you forget to attach, you could have built that fan system, but you forgot to attach it to this HVAC system. That's probably what happened in there, right? Oh, here we go. I did put it in there. I like to put in here the failed ones so that you can see. I go in there and I make systems fail so I can get all these examples. But in this one, it says that fan 4 fails, and it fails because the energy index for a VAV system has to be a 0.95 or higher. Now, the one thing it doesn't show in there is you have no idea what inputs were actually put in there. And sometimes, as you're packing things up, you don't think about, did I look to see if it was the past one or not? But many people, because that section of the code isn't thought about, don't always show up. All right, let's talk. Any questions about this section? How many of you feel maybe more confident if you see a set of plans out in the field, contractor designing, plans examiner, that you might go ahead and take a look at 403.8 section and be like, I can do this. All right, we got Jeff back there. Awesome. Now you guys know who to send it to. You got the math, you got the report, you're doing good. All right, fault detection and diagnostic. We talked about this as part of the requirement for the economizer. That was the fault diagnostic and detection and diagnostic that was associated with an economizer. This is for systems, the overall. But it's only for systems that happen to be serving a very large square footage. So if it's serving 100,000 square feet, then we have to comply with C403.2.3. So then you're going to have basically where it's the system as a whole is connected to somebody, or the other side of it, that's going to communicate with it that says, hey, I'm having some issues. The fan isn't working. It's not initiating as it should, or the thermostat isn't, turning it on. I don't know. I'm making things up here. But what it does do is it really monitors what's going on with that system as a whole. It reports it to something on the other end, whether it's building management. I can't think of anything at the moment. I had the opportunity to go to the University of Arizona, Tucson. I think that's the right one. It was in Tucson. And so I loved it because their entire campus down there, or at least the sections we were viewing, was sustainable. So they did a whole lot of I know you guys are like, but it was like rainwater harvesting, because they can do that there. And they had so many energy efficiency components in it, which is why we were touring it. But the big thing is, I loved going into this room because they had this wonderful, building management system that dealt with the entire campus. And so they were showing it. They're like, yeah, we can look at this building. It lets us know this system's working, or, hey, we're going to raise the temperature lower, just having a great time. I had my camera, had my good camera. And he's like, you can, we'll do this, but you're not allowed to take any pictures of it. And I'm like, oh, I would love to have had a picture. That thing was amazing. Anyway, the whole idea of it and why they obviously had it is because it allowed them to keep track of what's going on and fix any problems that are happening, because sometimes maybe you're noticing, hey, our utility bills are really high. Why is our utility bills really high? Until our utility bills get really high, if you don't have a system in place to let you know something's wrong, it's not until we get the utility bill that we pay attention to it. And it's not even the first utility, typically, it's not the first utility bill, right? Because it's like, maybe we had more people in the building, right? Using the bathroom, so we heated up a lot more water. It isn't until that second or third one, once it becomes a consistent measure, that we're like, something's going on here. And so this allows for it to happen much faster than waiting for utility bills to come out. All right. This is the section that I like to call, what can I do no matter who I am in this process, right? Everybody's like, I can ensure that there's a thermostat. Absolutely. So a thermostat is required in every zone, right? It's there obviously to monitor temperatures, turn things on, turn it off, but it's also there if we have humidification and dehumidification, or we have both, that we have controls that are going to be provided for that. So we have to have thermostats, obviously, for a couple of reasons, but in this instance, for one of the two. Now there is an exception here. And the exception I want to talk about is when we have independent perimeter systems that are installed. And the whole purpose of why they're being installed is because right here we have this system and then we have the rest of the building or the rest of the room. Why do we have something here and then something here? We're trying to offset our thermal envelope because guess what? When this got into the code way back when, and it was into 90.1, long before IECC was ever created, is because we had horrific thermal envelopes. So we had to offset what our windows were doing to the structure. So you had kind of like two systems going on. So in that instance, you're going to have it where you got something controlling the perimeter and then the one that's taking care of the true system, right? Now, heat pumps are pretty prevalent. How many of you are installing heat pumps or having designs brought to you for heat pumps? Yeah. So heat pumps, there is the idea for that supplementary heat. What the code requires is that basically you have controls involved that when that heat pump is just fine operating on its own, that it's the one operating. But in these particular instances, and we'll talk about that in just a second, this is when it's permitted that the supplementary heat can be kicking on, which a lot of times what is being used, electric resistance, which of course we're trying to kind of get away from. But the times that it says that it should be activated is when the vapor compressor cycle cannot provide the amount of heat that there is a demand for by what the thermostat is asking. It also says when it is operating in defrost mode, right? We've probably all seen those pictures, or we've all gone to the sites where the location of where that heat pump was maybe not thought of all that well, right? It's right next to a downspout. It's on the north side of the building. You contribute all those things in and you have a higher potential and we've probably seen it where they're iced over. Maybe you guys haven't. I've seen a lot of pictures of them. So when we are in defrost mode, then the supplemental heat can come on. If the compressor cycle malfunctions, then it can kick on, or if the thermostat malfunctions, then it can kick on. Anybody seeing this being done out in the field? Are you? It's actually been in the code for a while, but I think it's probably hitting more of an impact now because of all the focus in installing those heat pumps that they're like, oh wait, I remember seeing heat pump in the code, and so they're like, oh yeah, this is a simple one to comply with. All right, next thing is really talking about those thermostats, right? So there's a requirement that when you have a single thermostat that happens to be controlling both the heating system and the cooling system, that we have to ensure that we have set points for that. Whatever those set points are, you have to have a dead band of at least 5 degrees. Anybody know why they want it at least 5 degrees? The idea is we want to ensure that we aren't triggering the heating and cooling system to be on at the same time. Or my favorite is, and I shouldn't say favorite, I'll loosely say favorite, is imagine this, I go to hotels a lot. My favorite thing is I'll have the temperature in the room set at 70 degrees. It's cold outside, so I want the heat to kick on. If for some reason it, gets up to 70 degrees and maybe you have something else going on and it gets a little bit warmer because the drapes are open and the sun's coming in and it's hitting that thermostat, I've been in the room where then the air conditioner comes on because the set points weren't enough. The heat is up to 70, the set point for the cooling is 63. So then, or 68, so it just keeps going back and forth, and it drives me nuts because I don't have the ability most of the time to adjust it. And it just absolutely drives me bonkers. Yes?
And you're the one that calls the engineering department.
Am I the one that calls them? I have not necessarily done that, no. Now, I probably should, but no, I just suck it up. I suck it up. I travel with a heating pad. So sometimes if I figure out what the set point is for the heating and cooling, I can put it there and I can sit on a heating pad if I need to. But yeah, although somebody says, you spend a lot of money at hotels, you should be, semi-comfortable. I'm like, you're right. That's why the energy code is so important. Comfortability, the C word, because that's so subjective. But when we talk about comfortability, this is the part of the code that really impacts that, right? All right. Oh, yes. So the minimum deadband of 1 degree when the set points are adjusted, right? So when I go in, it goes up and down by 1 degree. So it can't like jump. There are a couple exceptions for this section. One is that it's dealing with things like hotels or multifamily where the occupants control their environment. How many of you have had that, you're in a hotel room and you have that lovely PTAC system in there where you get to control it? In theory, it's an exception. I still have issues with them on occasion, not all the time, but on occasion. And then exception 2 is focused on occupancies that have very specific temperature needs. It says, like hospitals, can you think of anything else that might have set temperature needs? Refrigeration warehouses, absolutely. Manufacturing, oh, that's a big one. I actually was consulting on a project for this particular manufacturing. It was in Colorado, I'm not going to tell you where. None of you guys were involved, I will tell you that. And so the design is, because for what it is, there's a requirement, right, in the thermal envelope section that says, hey, you have to have skylights. And manufacturing is part of it. Well, what they were manufacturing was would have a reaction with UV light. So they were asking for to not have skylights in their manufacturing area because it would cause damage to the materials, which was food, by the way, that was going to be processed. And ultimately the building department didn't give them that exception for it. They said, nope, you got to install it. And I was like, oh, that's bad. So they were trying to come up with all these solutions. They're like, maybe we can, put these things, going up there after they get their certificate of occupancy and everything, because they're like, we can't have sunlight. Actually, we won't be able to manufacture this because it degrades it or whatever. Not contaminated it, but this is one of those times that I was like, I agree, you should follow the letter of the code, but there also should be common sense. And they had, documentation that talked about how sunlight will degrade or whatever it is to it. And I'm like, I'd accept it. Like if you were in my jurisdiction, I'd allow it. It's not across the board carte blanche, but if you can prove to me that there's a problem with it, I have no problem. All right, so we talked about when a single thermostat is controlling two systems. What if we have two thermostats? Each of them are controlling a cooling system and a heating system. We still kind of have the same concept for it, right? We don't want the heating system to kick on when the cooling system is kicking on. So there has to be something involved with it that's going to prevent them from that. It could be a switch. They could use a digital direct control system. Basically, right, we have this system and then we have our operating system here. That operating system says, no, we have it programmed that the cooling thermostat turns on at this point and the heating does. So there just has to be something there that's going to ensure that we don't have both systems triggering because we have two separate thermostats now, which is a little bit, I would say, more tricky, because if you have a single thermostat, you have a little bit better control, but that when you have two thermostats, keeping track of that can be lots of fun. All right. We're continuing with our thermostatic controls, and you are permitted by code to heat or cool your vestibules. So when this came into the code, the whole reason why is this particular person who submitted this stated that they needed to heat the vestibules because the vestibules are required to have sprinkler head in there. And that sprinkler head, we want to ensure we don't have frozen and broken pipes. So they said we want to heat that vestibule, not a whole lot, but enough that we aren't freezing the pipes. And then, of course, in the process, people are like, oh, well, if you can heat it, then you should be able to cool it. Even though the whole idea of that vestibule is not to be a buffer zone. I mean, it is, but it's not to be heated and cooled. The whole reason, which is why I bring it to you, is the whole reason is that they wanted to heat it just enough to ensure that it doesn't freeze pipes. So, with that being said, what this section tells you is, yeah, you can heat or cool your vestibule. You can only heat it to 60 degrees or only cool it to 85 degrees. But when you do that, you must have a thermostat in that vestibule that controls that vestibule. Now, I mentioned I visit a lot of hotels. I visit a lot of places all over the country. How many times do you think that vestibule is heated or cooled?
100%.
I would say 99.9%. I think there's one that I can think of, but only that one right off the top of my head. Now, question then becomes, how many times do I see a thermostat located in that vestibule as required? I have 2 pictures of a vestibule who actually have a thermostat located in that vestibule. Every time I walk into a vestibule, that is the first thing I looked at. In fact, at the hotel I stayed at, I looked for it too. They had lots of gadgets everywhere, no thermostat, but they were heating it. And maybe it's on a direct digital system that has it in there that's going to control it, but it should have a thermostat located in that vestibule to determine, right? So, this is always a fun one for me. So here we have a unit heater that's located in this vestibule. And then if we look at one, it gives us all this information here. I'm not going to make you try to read it because nobody can read it. I can't read it. But the great thing is they gave me a sequence of operation. Now, on these plans. Do you know how many times I see on a plan and a vestibule that has the thermostat on it? Almost all the time. Do I see it out in the field? Somewhere it's getting lost in translation. So then I get this sequence of operation that tells me how it's going to operate. Well, I'm not going to try to read it there. I'm going to try to read it here. So if we read what the notes say, it says, provide a wall-mounted, as shown on drawings, thermostat to actually open the normally open two-way control valve and cycle the fan motor to maintain the thermostat set point. When the outdoor air temperature reaches 45 degrees or above, the fan and heating coil shall be locked out. Do what we saw on the plans and what we see in those notes, do they meet the requirements for the code? What the code asks for? How many of you say yes? Raise your hand. Remember, get out of the gym. All right, how many of you say no? Raise your hand. How many of you aren't sure? Raise your hand. This is one of those times that everybody who raised their hand was correct, because they're required to have a thermostat. They provided a thermostat. Now, they did talk about temperatures, but what they forgot to tell us is that they could only heat to 60 degrees and only cool to 80 degrees. Now, one thing that they added to it, which is kind of, in my opinion, a bonus, is they thought about it. The second note that says, hey, when it's 45 degrees outside, we probably don't need to heat or cool the vestibule. And so, we're not going to worry about it. Now, I'll tell you, this sequence of operation, I still look for something better, and this has been the best demonstration. And I have used this example for so many years. So I'm hoping one day to have a new one, because I get something on a set of plans that I'm like, I can throw this one out and say, hey, or show this one and say, here, look, here's a really good one. So just throwing that out there. All right. Here's the end of the thermostatic controls. So this one is dealing, who was saying that they have a lot of boilers? Oh, yes. So boilers. In this one, it's saying that you have to have controls, obviously, for when you're going to utilize the boiler, but those controls have to be based on that outdoor temperature. And the reason for that is sometimes we have boilers that are not only heating a space, it's also being used for domestic water heating, right? So it might be 90 degrees outside, but there's a demand for some hot water. And so because of that, they want to ensure that just because outside it's 90 degrees, inside it happens to be 65 degrees, because they have the air conditioner on, that the boiler doesn't kick on. So that's kind of the idea there. It's a version of the thermostat that it's like, this is how the boiler set points kind of work, kind of deal. So now, here is the fun one. So no matter what type of system you have, these controls have to do a variable of things. So the first one is our off-hour controls. Now you can use a programmable system on that. You can use a timer on it, but basically you're going to have a time where it's shut off because nobody's here, kind of deal. Now, there are some exceptions with it if the zones are operating continuously. If you happen to have a HVAC load that's less than 6,800 BTUs, and it happens to have a manual shut off, and then it has it with ready access. Remember, That just means that it doesn't have to be in the accessible reach ranges. It just has to be that it's not 11 feet in the air. It has to be where Hope would not kill herself trying to shut it off. That's basically, so think of it that way. Will Hope kill herself if she tried to shut this system off? And you might say, you know, she might. Let's see, right? Since she's providing us with all this fun. Again, thermostatic setback. And so this is really setting it back when it's kind of not in use. And basically what they want to do is they're going to have it, allow it to go all the way up to 85 degrees or all the way down to 55 degrees. And then, excuse me, the idea is we don't want it to get so far gone that when the system has to kick back on, it has to work so much harder for it, right? That's kind of the idea behind it. Now, this is our automatic setback and shutdown. So again, this is one of those times that you can have a timer, you can have a automatic, you know, control system because you have the lovely little computer system with it. And what it has to have the capability of doing is demonstrating that it can start and stop for 7 schedules per week, right? Basically, you have a schedule for Monday through Sunday. You have to have some sort of backup ability to it, that programming, whatever it's going to be, can be maintained for a minimum of 10 hours if the power happens to be interrupted. Because what happens if that programming isn't remembered, right? And the power's out for, 12 hours, 10 hours, whatever it is, or 1 hour. How many of you would even think about, hey, I wonder if my system is going to continue running the correct way? It's not necessarily something that's thought about, and nobody wants to keep having somebody come out and reprogram it, right? Because I know I wouldn't be able to program it, and sure as heck, I would not send my husband out there to program it because he can't even handle our thermostat at home. So he would not be out there. The other thing is you also have to have override switches. That override switch is going to allow for kind of like to skip the programming, but only for a maximum of 2 hours. And then again, the timer to operate the system for 2 hours. And then you have to have it where you're thinking about, and it's designed for the occupancy of that area or building. Now another one is, this one is kind of new, but not new. In the earlier editions, it had the optimum stop. And in the 21, they said, well, if we're going to stop it, shouldn't we also require for it to start? And so they added the word start on here to ensure that when you automatically stop it, you can also automatically start it. Because there was apparently a question about whether that was permitted. So now it's there. So you're going to have a schedule for it. And basically that schedule revolves around when people are going to occupy the structure or the room or whatever the case may be. So that's how you're going to design that. Now the controls are required in this particular instance. It's only done to 2 degrees. So it's not completely stopping it, not completely starting it, right? So the idea is basically you're either increasing what your cooling number is going to be or decreasing what your heating number is going to be. All right, I love this one. Demand control ventilation. So the idea of this is when you go into the IMC, I have the wrong table up there. When you go into the IMC and you have an occupancy density of the 15, right? That lovely table that we all love. And it's a single zone system with an economizer. Then you are required to do demand controlled ventilation. And basically what it is a couple of dampers, right? So we have air going through the system. This room is not showing a lot of CO2, and there's no demand for ventilation coming in here. But this room has a ton of people in there. And so there is a need for ventilation. So basically, the system going into this room has a damper that shuts it off, and this damper opens up to allow all the ventilation to go in a location that it makes sense. So a great example of this is, let's look at this airport. So, because everybody was stuck here at security, this is where I was in line. I had to go all the way through here, down through all the stairs, and then start doing all of this down here. They said this is going to be about a 2.5, 3 hour wait to get through security. So I thought it was a great example to take a picture of, because do you think maybe there might be a high demand for ventilation going on in that area? Probably. Although it might have been nice, maybe if a few people passed out from lack of oxygen, might have made things a little bit more exciting. Not that you want excitement at an airport. But because everybody was here, it's kind of dead in the concourse, right? It's not the same airport. This was really late at night. But the concept is the same, right? So we need all the ventilation going on here, but we might not need it in another location because there's no big demand for it to happen there. Just because we gotta have more fun with ventilation here. This is one of those times that I'm gonna tell you what the code says, and then I'm gonna let you know what you need to do. So in this instance, for enclosed parking garages, you do still have to install some detectors on here. It says monoxide and nitrogen dioxide detectors integrated with controls. Now, it says the controls to operate fans at 50% or less of the design capacity, or controls to operate fans intermittently less than 20% of occupied time to keep levels of contaminants at acceptable levels found in the IMC. When this section came into the code, there is a gentleman who lives in the world of the IMC and the mechanical code. And I have a lot of respect for him. And if he says something that there's an issue, I'll listen to it, because it's not somebody who is out there for a type of gain. He just wants the best code possible type of deal. Unfortunately, these two items that I just mentioned made it into the code. I am going to say, while the energy code does say this, what you need to do is follow the parameters of the IMC, because what he said is that this contradicts what's in the IMC. So in this particular instance, I'm all about the energy code, but we want to ensure that we aren't creating an issue. So follow what the energy or the mechanical code says as far as the operating situation. That doesn't mean ignore it altogether. Just means make sure you're ensuring that you're meeting that criteria. But there are some things that you can follow, right? So if the sensors fail to exhaust, fans are to operate continuously. That's a good feature to have. Limited exhaust must qualify as an exception. These are two of the exceptions that we're going to find within the system. All right, energy recovery. This is another one of those sections that I think gets cumbersome in trying to figure out. And I could be wrong. Could just be, you know, hope speaking, but let's talk about energy recovery. Anybody know what type of fans can be involved with energy recovery? Or are you like, Hope, could you just move the slide so you could tell us? All right. So one of the types that you can have is a energy recovery wheel. I will say on the plans, probably 9 times out of 10, I would almost say 10, except for I can recall one set of plans that had something to the contrary. But most of the time, they call out the use of an energy recovery wheel. A lot of times where I see that is in the equipment schedule itself. It'll have a little note saying, hey, this is what we're doing. The next one is, which probably seems a little familiar because it's the concept that we see a lot on the residential side, right, is the flat plate. And that's where you have air coming in this, you know, from outside coming in, and then you have the air from inside going out, and they're kind of preconditioning each other, right, helping out with that. And then we have our energy recovery that happens to be a runaround loop. I have never seen this system. I don't have a lot of experience with it. Anna actually said she's only seen one, I think she said, in her entire mechanical engineering career. So it's probably not one that you would see a lot, but it is out there. Now, when these come into play, so if you are a non-transient dwelling unit, which is that 30-day, right? That's the magic number. So when you are non-transient dwelling unit, you have to have an outdoor air recovery ventilation system. So you're going to utilize one of those 3 options in there. Now, what's important is with this system, for the non-transient, what we're going to do is it's the entropy ratio that really has an impact. So when we're talking about our cooling, the entropy recovery ratio has to be at least 50% at the cooling design temperature. Now, for our heating, the system has to have a 60% for the heating design conditions. Now, there are some exemptions, and the last exemption here, this is the one that we're going to pay attention to, because it says for our cooling design, we don't have to pay attention to it. What they want you to pay attention to is the heating, because they understand heating is something that you do up here, and that cooling is not as a big deal as the heating would be. So that's why this climate zone happens to be exempt from it. Now, if you are a space that is not a non-transient dwelling unit, now you get to have the fun of playing with some tables. You still have to have a system, but now you get to play with some of the tables. So the first table you're going to deal with is the C403.7.4.2 parentheses 1, and then the second one is parentheses 2. Now, the difference between those 2 tables really deals with the amount of hours per year that the system is actually going to operate. So that lets you know which table you're going to follow. Not that you have to follow both tables, just which category you fall into, right? So if you're a January to December, you're probably going to exceed the 8,000 hours, and you're going to follow the one that exceeds 8,000 hours. If you're only something that's made September, you might be less than 8,000 hours, so you're going to follow the other table. You have to, this says you have to have an energy recovery system, which I just said. But what it will say is that your enthalpy recovery ratios have to be at least 50% at whatever the design conditions are. And typically, you know, that's residentially, it's really easy because they put that sticker on it that says, hey, my enthalpy is going to be, you know, 63% at design temperature of 65 degrees, you know, or it's at 35 degrees, 30 degrees, whatever it is. It has that on there. This is one where you probably need some documentation that's supplemental. Whenever we talk about commercial, very rarely do they plaster it with a sticker like they do residentially that makes it really easy for us. Typically, we have to have a separate document to let us know what it's going to be. And then if by chance you happen to have an air economizer, then the energy recovery system also has to have a bypass or have some sort of control that's going to allow for the economizer to work instead. Now here is the table. So this is if you are less than 8,000 hours. We're going to be looking, let's see, anybody 6B in here? Or are we all 7 for our climate zones?
I think 6 and 6A.
Okay. Well, so we're going to look at this row here. This is the row that you're going to look at. And so basically, when you have, this gets so, some of these tables get so incredibly complicated and convoluted that it's really hard to describe. So what they're saying is for the percentage of outdoor air that's going to be utilized when you're talking about the full air design. So let's say you were going to do 100 CFM and 10% is outside air, right? So, or yeah, so 10 CFM. So that's 10%. So what we're then going to do, our 10% is saying that's the percentage that's coming from outdoor air into the system when we're designing it. So we would then look at this column, come down here, and it says that our design supply fan airflow rate is no less than 28,000 for it. This is all the people who raised their hands that said they loved math. Section 403 is for you. So here's another one fun example of having all that in there. Now, typically when I get plans that starts talking about this, all they say is, I don't know, maybe the fan system's going to be at 28,000 and it's 10%. I'm like, okay, I got it. That means that's the correct row. They looked at the correct row, just like I can. And now, for this one, this is if you are operating less than 8,000 hours per year. This is the table that we would look at. So for us, we're going to look at this row down here. It's the same concept, how much outdoor air is going to be done, and then what is our design fan flow rate is what we're permitted, right? All right, now let's talk about if we happen to be a non-transient, oops, did I just skip? Dwelling unit for exceptions. This is the exception to this, and this happens to be if the mechanical code prohibits it. Don't know why we'd have to say that here because, I don't know, if the IMC told me in this instance you can't have one, I'm not going to ask them to put it in. There's probably a good reason why they're saying, hey, don't do it. I've gotten old enough in my wise years that if somebody says it's not a good idea to do it, I'm probably going to listen to them because they probably know better than me. 20 years ago, That's a whole different conversation. All right, laboratories. Now, the laboratories do have some criteria about what they need to have to qualify for it. If you're only heating the space and you're not getting to 60 degrees, they call it good. Or if you happen to have 60% of your outdoor heating energy is provided by site recovered or solar site solar energy. If you're, well, the next one we don't have to worry about, but the enthalpy recovery requirements at cooling design, you don't have to worry about because 6B. The other one is if you have a system requiring humidification that's going to be employed when there is cooling going on. If the largest source of air exhaust at a single location of the exterior of the building is 75% of the design outdoor air, if it's going to operate less than 20 hours per week, and systems that are exhausting toxic, flammable, or paint, that's when you try to put those two words together, or corrosive fumes or dust, right? Energy code says, hey, those are all things that we shouldn't mess with. Have at it and have fun, right? And then commercial kitchen hoods. So this is one of my favorite sections. So if you are a hotel and you happen to be, or we'll just say an R1, I just said hotel. But if you have 50 or more guest rooms, you have to have controls for your heating and cooling systems, and they have to be provided in the fashion that I'm going to tell you. You also have to have the use of a key card in this system, or you can use a key card, right? You know, you put your little room key in the little device and then things turn on for you. All right, so the first one. This is when you have guest rooms, and those guest rooms are rented, but they are not yet occupied. In this one, what you're going to do is you're going to have some sort of control that's going to either raise the temperature for cooling or lower the temperature for heating to by 4 degrees. And this happens to be activation 30 minutes after the people have left. So basically, you know, if I was at the hotel, I stayed there, I'm coming here to teach, and then I'm going to go back. In theory, they should have a system in place that raises, we'll say lowers because it's kind of cold outside, lowers the temperature by 4 degrees until I get there. The second one is if the room is not rented or occupied, now what you're going to do is you're going to change the cooling temperature to 80 degrees, and you're going to change the heating to be not more than 60 degrees, right? So you're kind of keeping it so that it's not crazy for the system to try to get to, you know, a decent, comfortable when nobody's there, because that room could stay vacant for weeks, right? And if it's going to stay vacant for weeks, we probably don't need to heat it to 70 degrees. It could be at 60 and be fine until it's time. You have to have, or you could use a network guest room system that's going to reset everything and do that for you. So how many of you have stayed at a hotel? Anyone? Okay. How many times have they asked you, when do you plan on arriving? And you're like, well, why are they asking me that? Do you know why they're asking you that? Because they have this system, and they're trying to ensure that if you're going to be there at 8 o'clock, they're like, okay, at 7 o'clock, we're going to put it to a temperature that makes sense for the time of year and location and everything, because you're not going to be there till 8 o'clock, but when you walk into the room, in theory, it's a comfortable temperature. But for all that time prior to an hour of your arrival, it didn't need to be at that temperature. And that's really what they're doing. They're not prying and trying to be, obtrusive into your life. They're just wanting to make sure that your stay gets to be comfortable. And then the third one is occupied rooms, and they're being occupied at the time. So in theory, last night when I was at the hotel room, the system has no control over it. I get to determine what I feel is comfortable for my desires, right? All right. Now, it doesn't just apply to the heating and cooling systems. It also applies to the ventilation systems. So in this particular instance, you have to have controls that basically within 20 minutes of us leaving, the ventilation systems basically shut off. So there was a time, we're talking many, many years ago, probably before this came into the code, honestly. I stayed at a hotel in Wisconsin. Now, I will tell you, they are not anywhere, their code is not where we're at, okay? Which is why what I'm going to tell you is so impressive to me. Is I walk into the room, there's this wonderful sign. Now, I will tell you, my husband, came with me because we were going to a Packers game. Go Pack, go. Absolutely. I know, don't worry. I take care of him too. So we're getting to this hotel room. There's a sign. It says, hey, our mechanical systems, or I think they said furnace and AC, because they're using terminology that most people are going to associate with, is on an occupancy sensor. It will kick on within 15, you'll feel it within 15 minutes of you entering the room. Now, I talk about my husband for a couple of reasons. One is we've lived out here for all these years. I don't know if you know this, it's really dry here. We went back to Green Bay in September. It's really, really humid there. And that makes the heat kind of feel a little bit worse, especially for him. So he is just, profusely sweating like crazy. And he's like, oh, we got to cool it down. He's just all flustered. I saw the sign and he's like, you got to call the front. It's not working. Sometimes you just know it's better. Okay, I'll call the front desk. Because no matter what you say, it isn't going to make, anything better. So I call the front desk and I say, hey, it appears. And he goes, yes, it's on an occupancy sensor. You should be filling it here, shortly. Because he obviously checked us in. So he knows how long it's been, probably, since we got to the room. And he goes, it'll kick in. And so I relayed the message. And then, my husband went into the bathroom and was, putting things away. And since he was out of earshot, I said, so question for you. How many times do you get this call in the day? And he goes, actually, I get quite a few on it. And I said, so has anybody, complained to you about it or anything of that? And he goes, no, once I explain, especially when I say energy efficiency of it, he goes, nobody questions me after that. And I'm like, oh, cool. So, we have this conversation. I said, okay, great, I'll let you go. But I was really excited about it because, the energy efficiency geek inside of me just had a great time. But it also had controls for ventilation. Anybody think about a time when that could be an issue? What about when you're sleeping and you don't move and it shuts off and then you roll over and all of a sudden you hear the system go, you're like, oh, what the heck was that? So, all throughout the night, we kept waking up because the ventilation system would kick in because it would shut off because we didn't move while we were sleeping, and then we'd roll over and it kick in. So, we're working on it. There are things. Anyway, you guys got to hear that wonderful story. Aren't you guys so glad you came today to hear that story? It makes up for all the boring things I talked about fans.
See the Pac-Man as well.
Oh my gosh. I went and saw my nemesis of the Vikings. There's only one team that I will root for the Broncos to beat, and it's the Vikings. Unfortunately, we tied. But I've gone through enough therapy that I'm okay now. So here's the section that we talked about earlier, that there's quite a few references that steer you here. This tells you you must utilize a Class 1 motorized damper for all of your openings. It also has to demonstrate that it has an air leakage rate that does not exceed 4 CFM per square foot. It also has to be a labeled damper. Now, there are a couple of exceptions if you happen to be 2 stories or less, or if you exhaust less than 300 CFM. It also says it's not required in climate zone 2, but we are not 2, so it's required. What was I going to ask you guys? Have you guys ever seen these? So I was up in Aspen. No, not in Aspen. I was in Vail. So we were going for a walk. It was a family deal, and we're going for a walk around the hotel. So this is the actual dampers for a hotel, the exhaust for a hotel, right? I'm so excited. I'm taking these pictures because I'm watching it open up and all that. So I'm taking these pictures, and what I should have done was taken video of it. I'm like, oh, I keep missing great opportunities to do videos, but that's a real live one. I got to see them open up and work and function and all that good stuff. So not uncommon to just see it as a note on a set of plans. A lot of systems now already have them kind of incorporated into it. I brought this in here to talk about is the low capacity fans. This is very similar to what we see on the residential side of the code, but it does kick in here because there may be times that it hits this. And what I would say is, while this is a requirement, and you'll notice that the table is all blue, meaning it was new in the 21 for the commercial side. It's been in the residential side forever and a day with these particular values. In fact, they expanded onto other ones that wouldn't necessarily translate over here because this is more commercial than obviously residential. But this is one of those times that I have noticed the manufacturing industry has again taken hold of the energy code, because why not? Are you going to produce something that can't be utilized? No, you're going to produce something that is utilized. So while there's these requirements, I'll be honest with you, I have yet to see a product not meet these. So I'm not saying don't pay attention to it by any means, but if you have to focus between A or B, if this is A, focus on B, because this is almost a gimme. How many are seeing large ceiling fans, right? I see these a lot in gyms, like exercise locations, right? Or warehouses. I'm seeing it now in those big, enormous warehouses where they're utilizing these. And so all the energy code is asking is that they have to be tested and labeled in accordance with AMCA 230. So that's almost a real easy one to take a look at. So this section, I have it in here, but it's again one of those sections that I would say more times than not it's looked at, right? Is the ductwork inside the thermal envelope, outside the thermal envelope? If it's inside the thermal envelope, all right, there's not much we have to do. But if it's outside, and depending on where it is outside, then we got to insulate them. And well, for you here, it would be an R8 if it's you're separating conditioned space from unconditioned space or interior. And then we have all these here. Now, the one I love is the ducts located underground. Typically, that's for those systems like a campus, right? A college campus where they've got the mechanical system that's going from building to building to building because they have this enormous cooling tower, right? So that's what they're talking about, not necessarily we have a building and they're putting some ductwork in their crawl space or below grade space. I just want to make sure that's clear. And then, you know, let's seal things up, which makes sense because this is what we're trying to ensure. And everyone's like, well, that's a patch. You're right. It still would be required to be sealed up because I don't know if you notice all that lovely discolorization. So this, my husband and I noticed that the food at this restaurant, the quality had kind of fallen off over the last couple of years. So we sit down, I get the spot right here. All I can do is stare at that. And of course I take a picture of it. And it's one of those open kitchen things. So do you know what was directly under here? Where they were preparing my food. So I apparently got some extra seasoning to my steak. So, and I got it for free. So yeah. We don't go there anymore. Now let's talk about piping insulation. So when we have, now this applies to, this is in the mechanical section, but even in the 404, the service water section, when it talks about insulating, it sends you to this table, or the table we're going to talk about here in a minute. And so basically, when you have any sort of mechanical piping and you are going to insulate that type of system. So boilers, obviously, you're going to insulate like crazy. Here are the exceptions to it. Here are the exceptions to it. You know, if it's already installed in the, you know, part of the system itself, we aren't going to require you to insulate the piping inside that boiler. We aren't touching that boiler, but once it's outside of it, we're going to do it. All right. How many of you have played around with this table before and tried to figure it out? How many of you look at the table and say, this is so convoluted and such a pain in the butt? I would say it's convoluted and a pain in the butt. So how it works is this is the column for the temperature of the fluid, whatever it is, right, inside the piping itself or tubing. Over here is talking about the size of the pipe or the tubing. And then this section, part of the table, is telling us how many inches of insulation is required. Now, let's say we are 110 degrees and we are 2 inches of pipe. How much insulation is required? So if we come here, because 2 is greater than 1.5, less than 4, it's 1.5 inches. So if we look at this one and all of these numbers here, or these numbers here, the main difference we have from the different rows is here, right? And this is because our insulation is incredibly important now. Because whether it's a 1/2 inch for a 1-inch pipe or a 1/2 inch for more than 1 inch to 1.5 inch, they're both 1/2 inches. So it doesn't make sense, right? Because we have a higher temperature, bigger pipe, and it has the same amount of insulation. Where the difference is here. So when they're talking about a 1/2, where are we here? They were talking about 1.5 inches. This 1.5 inches, the insulation has to demonstrate that it has a conductivity that's between a 0.21 and a 0.28 at a temperature of 100 degrees. Did I put it in here? Give me 2 seconds because I'm going to show you something. So how often have you guys seen something of that nature in it? I think I have an example of that in this class. So let's do this. Nope. So typically we're going to find that information. It's not put necessarily on the actual insulation itself. What I would be doing is on a set of plans, I have it's called out for me. There we go. Sorry, I should have added that to here. Here we go. Ah, that didn't do it. Sorry guys, I want to show you this example because I think this really does help in trying to understand that. Okay, I've clicked on this. Now go to the current slide. There we go. Okay, so here's an example on a set of plans. This is calling out, okay, we have piping, here's our degrees. It's kind of a carbon copy of the table in a sense, because it says we have these 4 different temperatures. And for these 4 different temperatures, they had pipe sizes, tubing sizes that went through all of these. So it actually was needed in it, but it also had these notes. Now, down here for these notes, it talks about the minimum thermal conductivity, K, which is often what they call for the mean temperature of it, is going to be a 0.27 at 75 degrees. And then this one is the fiberglass is at a 0.23 at 75 degrees. So if we came back here and a 0.25 at 75 degrees does not work for our 110, but if it was temperatures between 40 and 60 degrees, it would meet that. So you should be getting something of this nature that correlates with your piping and tubing insulation, because here's an example, right? We can't really see anything here. You can't tell. But if you come over here, you have the product information for you, and it will tell you what is our, this gives us our mean temperature, right? And then we're looking at this one right here. So for we had to have it at 100 degrees, and it's showing a 0.24. If we come here for our 110, 100 degrees, and the 0.24 is between a 0.21 and 0.28. So see how that product, I don't even know what product it is, see how that product would work with what the code requirement is asking for that 110 degrees. Does that make sense? That's how I would typically see it. All right, let's talk about heating outside, because there's a lot of heating outside I see at hotels. So the first thing that when we talk about heating outside, it's got to be a radiant system, right? And then there has to be controls on it. So it's got to have an occupancy sensor or a timer on it. Basically, if nobody's going to be there, it's not on, because why do we need to heat the outside if nobody's there, right? So there's a great example of one. The sensor doesn't show up very well in that picture, but let's talk about swimming pools, because we all have hotels, right? And they all love to have swimming pools. So you are required for your swimming pools to make them energy efficient. To make them energy efficient is to ensure that you have a control that's going to, an on-off switch that's either part of the heater, or it can be mounted on the exterior of that heater, or mounted within 3 feet of that heater. And then if it is within 3 feet, it has to be in a location that's accessible. Not accessibility wise, just not 10 feet in the air, right? Whenever you have that on-off switch, it can't change the settings that the thermostat is at. You can't utilize a circuit breaker as your on-off switch. And if you're using a gas-powered heater, you can't have a continuous burning pilot light. You also have to have a time switch on it that's going to turn things on and off to a schedule, whatever that schedule would be. There is an exception for that if you're using solar powered or and waste heat recovery, which we didn't even get to. Waste, I love waste recovery. Anybody seen those systems? Yeah, if you ever get pictures of it, I love it. So you got this copper piping that's wrapped around the drain waste. So you're taking a shower, right? All that hot water is actually preheating the water before it even gets to the system that it's going to heat it. So basically, you're using your wastewater to heat the water that's going to be part of this. It's great. Anyway, so if you're part of it, or if the health department says, nope, you're going to have it on 24 hours. So a lot of times I'm seeing these electronic systems being utilized. Now, if you have an outdoor heated pool, now in technicality, the 21 just says a heated pool. You are required to have a cover on it. In the 24, what they do is further clarify it to say, hey, we're just talking about those outdoor pools having a vapor retarder cover on it. But in the 21, it still has it. And you have to have a vapor retarder pool cover on it unless you're using a heat pump to heat the water. You have an on-site renewable energy system with it. Now keep in mind too, that if you've adopted the energy code and you've adopted the swimming pool and spa code, those sections don't line up. So you need to determine which one you're going to utilize for compliance with it. Most people utilize the energy for it. They're like, well, the energy was set up for it. But in the pool and spa code, what is it, 308? 308 is an entire section dedicated to the energy requirements. All right, and portable spas, they've just got to comply with APSP 14. So you guys have been sitting there a really long time. Let's take a 5-minute break so you can recharge, and we'll hit lighting. That's the end of mechanical, okay? So your brains can now explode. One of those times where there's a little bit of a interesting dynamic between the commercial side and the residential side. So this section is referring to lighting that happens to be inside a dwelling unit. So those multifamily projects, if you're on the residential side of the code, it's 100% of them have to be high efficacy. In the commercial side of the code, they only have to be 90% high efficacy, so you still have a 10% leeway. Now, this is talking about the lighting that you'll find inside the dwelling unit and not the entirety of the project. So corridors and all of that are following a different parameter. This is just the dwelling units themselves. And keep in mind that the efficiencies for whether you're a lamp or a luminaire did change in this code cycle, both on the commercial and the residential side. All right, so we got to have controls. And there's quite a bit of requirements for the different types of controls that we are going to need. So you're going to ensure that all of these locations have controls except for these three areas. And the one I want you to pay attention to, and this is for future codes, a lot too, is areas that are designated as security or emergency areas that need to be lit up continuously. So that would be, I don't know, the entryway into a police station, right? Instead of it being like on an occupancy sensor that shuts down if nobody's there, there is a time and a place, but I want to make sure it's lit up all the time. For the 21, interior exit stairways, interior exit ramps, and exit passageways are currently exempt. Emergency egress lighting doesn't have to be on controls as long as it's not typically on. If it's, you know, lighting that's only there for egress, right, getting the people out of the building, it's not a requirement. So let's talk about our first type of sensor, our occupancy sensors. So as you can see with what's shown on the screen, these are all the locations that an occupancy sensor is required to be installed. In the 21, 10 is a new one. Corridors are required to have an occupancy sensor. So in this example, it shows an occupancy sensor for a space that's less than 300 square feet for our restrooms and our private offices. All of those are listed in that long list there. Well, it's not that long. It'll be much longer in the 24. Now, what our occupancy sensors have to do is if you're not an occupancy sensor for a warehouse or an open office or a corridor, all the other occupancy sensors have to shut off 20 minutes after the people have left. You can have a manual or an automatic on that's going to go to the 50%, and then you also have to have a manual control to turn it off. So in all the locations outside of warehouses, open offices, and corridors, it's shutting off completely. For a warehouse, you have to have all of the aisles on their own sensors, and they have to be independent also not only to the other aisles, but it has to be independent to the main open area of the place. In this one, we are only reducing the power down to 50% after everybody's left the space for 20 minutes. It does provide you the opportunity that if you aren't going to install an occupancy sensor, then it has to be on a time switch control. So it does give you a little bit of flexibility there. And then you do also have to provide a manual control for this. Now, open offices. This is a fun one, I think. So occupancy sensors are required when you have an open office. If the space happens to be less than 300 square feet, you're not necessarily complying with this, then you're going to go back to the main occupancy sensor where it's going to be, 50% after 20 minutes. You got to have the manual off, you know, all that fun stuff. But if the space is greater than 300 square feet, then you're going to follow all of these, which says that you're going to have a zone, and those zones can't be more than 600 square feet in that zone. You're going to shut off the general lighting after 20 minutes, and you can also have control zones that shut off within 20 minutes of everybody leaving. And then general lighting in each zone that's going to reduce the lighting to not more than 20% of the lighting within 20 minutes of people leaving. So this is a fun one, right? Because it kind of almost talks around in circles a little bit. So here's an example. I got these plans. I'm like, hey, you got to have an occupancy sensor in this open office. And they're like, we do. If you look at the letter, at the symbol for occupancy sensor, I'm letting you know which ones they control. Do you know how long I looked at those stupid plans? You know how you get black and white, blind? I was looking at them forever and a day. I'm like, there's no occupancy sensors. When he told me that and I went back and I pulled out the original plans, I'm looking at it and I'm like, wow, I must have been looking at the plans like this, right? All right, this is the new one that came into the 21. This is dealing with corridors and how the occupancy sensors and how they're going to function here. The big thing to keep in mind for a corridor, they are not shutting the lights off completely. They're only reducing it to 50% after nobody's been in that corridor for 20 minutes. Now, when it does reduce, it has to reduce uniformly. There is an exception in here. The exception is if at 50%, it's less than 2 foot candles of illumination at the darkest point on the floor. Why would they have that in there? Code minimum, yep. So keep that in mind. Because our lighting, bless you, has gotten so much better than it has in the past, this might be something that we'll have to pay attention to. So if it's not on an occupancy sensor out of that list, that doesn't mean all the other spaces, you know, are scot-free. They then have to have a time switch control. There's a few exceptions in here, right? Endanger occupant safety and security if it's required to have continuous lighting. Shop and laboratory classrooms, probably a good idea, right? We don't want the high school kid, you know, create a bomb inadvertently because the lights went out, right? And I just say create a bomb because they mix something to, you know, whatever. Anyway. So the functions that these time switches have to have is they have to have where it's a shut-off, automatic shut-off in the schedule. It's kind of like that thermostat, right? It's got to have the capability of a 7-day clock, different types throughout the week. It's got to have holidays built into it, because do we need the lights on if nobody's going to be in the building for Christmas Eve and Christmas or 4th of July or whatever the case may be? We need to shut it off. More importantly, it's got, well, not more importantly, but very importantly, it's got to have the capability of keeping that programming if the power is shut off, and it has to be able to keep it for at least 10 hours. There's an override switch that needs to be involved with it. That override switch is going to allow the power to be or the lights to be on, but for no more than 2 hours. It also talks about individual switches. You can have them, obviously, but they cannot control more than 5,000 square feet. And then we have some exceptions, right? Some of these exceptions deal with mall concourses, auditoriums, sale areas, manufacturing areas, sports arenas. Then it's not great, should be not greater, no great than 2 hours. That's great English, right? If using a captive key device, that's that lovely, I'm going to stick a card in this device and it leaves it on. So here's an example. Gave me, information this vestibule is going to be controlled via a time clock. It's going to turn on 1 hour prior to business opening, turn off 1 hour after, and provide a 2-hour override at the local wall station. So here's that local wall station that you can click the button. And there we go. That's it being installed. Yes?
From an inspector standpoint, what's the best way to verify this stuff as well as occupant sensor controls?
I am so glad you asked that. I didn't put it in here, but there is this wonderful section. It's in 408. 408 deals with commissioning and functional testing. So what I'm going to do as an inspector is I'm going to walk into the room. I'm going to ensure that there's a control. I'm going to ensure that I see the occupancy sensors. But where the mechanical system doesn't always require commissioning and testing, the lighting, no matter what, all of the controls are required to be commissioned. So me as an inspector, I'm going to ensure that the sensors are installed and in the right location. And I'm also going to require that report is provided to me before I sign off on the final electrical. That's how I handle it. But I love that you asked that. Because a lot of this stuff, I can see that it's there, but I don't have the equipment or the knowledge to know that this is going to turn off after 20 minutes. I can't stand outside of the room for 20 minutes and hope that the lights turn off. So that's how I deal with it.
That's where my concern was, just like, we don't have the time to wait around for these
Oh, yeah.
to turn off.
Yeah, wouldn't it be nice if we could just, pull up a chair, have a cup of coffee, eat a bagel, and wait for the lights to turn off? Can you imagine that in a hospital with all those rooms? So we luck out that 408 exists. Lighting reduction controls. This is basically what they're talking about here are dimmers. So this is also one of those fun ones. It says when an occupancy sensor is not installed, you will then have to have light reduction controls. Unless you have daylight responsive controls or you fall into the specific application controls. So there's a whole section that deals with times that specific application controls have to come into play. And then manual controls for the following, when you have one luminaire that's less than 60 watts, spaces that use less than 0.4 watts per square foot. And this is most importantly, corridors, lobbies, electrical rooms, and mechanical rooms. These three are incredibly important. Corridors got thrown in there because when this came in, you didn't know whether the corridor occupancy sensor was going to make it through, so they threw that in there so that if it didn't make it in the occupancy sensor, you weren't also doing light reduction controls there too. Now for the controls, they have to reduce lighting by at least 50%. You have to have a uniform pattern, and that needs to go where you're at full and then all the way down to off, right? So it's that idea of 10%, 20%, and all of that fun stuff. And that's where the continuous dimming control and how you're going to achieve that. You have one of the three options that's going on there. So even though they say light reduction controls, they now say right here dimming controls, which is what they're referring to. Daylight responsive controls. How many of you see this section and you think, oh my gosh, this is insane, I can't quite get it? Nobody? Oh. Well, this is a fun one. I love this section. So in the 21, previous editions, you only had one daylight zone. In the 21, you now have two daylight zones. You have your primary daylight zone and your secondary daylight zone. Basically, every fenestration creates a daylight zone, and it is required to be placed on the plan, so everybody's all aware of it. Typically, I see it on the electrical plans. I've only seen it once on the architectural plans. but it's typically taken care of by the electrical engineer there. And so any window, glass door, any glazing skylights creates, well, not skylights for side lit, but for our side lit daylight zones creates it as long as the window is at least 24 square feet. So if it's a really small window, it doesn't trigger a daylight zone, but basically anything else is going to trigger a daylight zone for us. In that, how you figure it out is it's incredibly important. Did I put it in here? I didn't put it in here. So how you figure it out is you go from the ground here, the floor, we're going to measure to the top of the window, and let's say it's 10 feet. Then you're going to lay it down, and that's the 10 feet from the glazing to inside the room. That's your primary daylight zone, and then you just double it again, and that's your secondary daylight zone. And why that's important is because if you have 150 watts of general lighting in your primary daylight zones, now you have to have daylight responsive controls. The other criteria that kicks daylight responsive controls in out of this section, there's other sections that require it, but in this section, is if you add your general lighting watts together and it equates to 300 in both your primary and secondary zone, then it triggers the daylight responsive control. So in the primary, if you had 149 watts, you wouldn't be required to have your daylight responsive controls. But if you have 149 in your primary and 151 in your secondary, now when you add the two together, you equal the 300. So now you get daylight responsive controls. All right, so when we have our daylight responsive controls, each zone is controlled independently. So our primary is controlled with a sensor, and the secondary is controlled with a different sensors, right? So we're ensuring, because right here we got a lot of light, but with it being 10 feet, you go 20 feet in, you might need a little bit more lighting than right next to that window, right? So that's kind of what they're ensuring, is that we don't want it to be dark here just because it's really light right next to the window. It has to be, they have the capability of dimming continuously, right? So when it's really light, it doesn't need to be on, but as the sun moves, it starts, getting more. Occupancy sensors reduce lighting in occupied areas for the code. Zones that are facing different directions. So a great example would be I don't know why I'm putting the pointer, but right there in the corner. We got a zone that's facing two different directions. So you'd have to have something that's dealing with the light coming in, with the light coming through this side, and then right here you're going to have a different one that's going to control it for when it's coming this side. Now, this is how you determine and figure it out. So like I said, you're going to measure from the floor to the top of the window. That gives us our depth of the daylight zone. And then here, it's supposed to be 1/2. It's not showing up with the line there. But it's 1/2 of the height of the window. So if it's 10 feet up, then for each side of the window, you're going to measure 5 feet in all of that. So here's an example of where they demonstrated the daylight zone. So no matter whether they're required to have daylight responsive controls, they have to place it on the plans. In this one, they said, hey, these zones only have 94 watts, so it doesn't trigger controls. In this one, you can see they did the primary and the secondary. And in this one, it says room-controlled closed-loop photocell daylight sensor. You can see that it has one in this zone, and one in this zone, one in this zone, one in this zone. Where there's an issue is this middle one, because they only have a single one. So they need an additional daylight responsive control in their primary zone right there. And then just in case, here's what it looks like. Here's the sensors and then the lovely controls. You can see it's showing different dimming on those controls. That's just what those lights show on that one. That's not how they all are. So here's the specific application one. So this one says you have to have an occupancy sensor or a time switch and a manual control. So for all of these sections, so we'll talk about this when you get to utilize the additional lighting option of the space by space method, you have to have occupancy sensors or a timer switch and a manual control for that additional lighting. Display cases and accents, lighting and display case, supplemental task lighting, lighting for sale and education, and display lighting for exhibits and galleries, museums, and monuments. Now, here's a really fun one. It continues to then say, sleeping unit control devices or systems to automatically turn off lighting and receptacles 20 minutes after everyone has gone. How many of you knew this was in the code for those hotels? Well, don't worry, in the 24, they make sure everybody knows that it's in there. But this has been in there for a while. Now it does talk about you have a couple of options instead of having it on, occupancy sensor type deal. You can do it where you have the key card control, where when you're in the room, you put your room key in there and it takes care of it for you. I kind of like that a little bit because I always lose my room key. And if I knew that it's just in that control, then it makes it really easy to find it when I want to leave. Lighting that's for plant growth or food warming. Task lighting for medical and dental purposes, they just have to have a manual control. Now, exterior lighting still has requirements for control. Now, there is some exceptions, lighting for covered vehicle entrances and exits, and that's dealing with that eye adaptation. Anybody gone into downtown Denver is notorious for it. You go down because all the parking's underground. You go down and it goes from light and then they have no light. And I don't know about you, but I put on my brake for my eyes to adjust because I'm like, I don't want to inadvertently hit somebody who's down there at the bottom of the hill because they're trying to get to their car or whatever. I've had people honk at me and I'm like, I'm really sorry, but I can't see. And I don't want to be on the news, right? So the first one is you have to have lighting that automatically shuts off when there's enough daylight. Here is light, I don't know if you noticed, but it's really blue in the background. That lighting should be off because there is an awful lot of lighting, sunlight present there. Building facade and landscape lighting. So this one is a fun one. So this one, you have to comply with this, both of these. So it shuts off an hour after business closes. And it turns on no later than or no earlier than 1 hour before it opens. The next one is if you don't fall under the requirement of when there's enough daylight, or you don't fall under the landscaping and building facade, then you have to comply with this one. This one says that you have to have control that's going to reduce it to 50% at one of the following times. So between midnight and 6 a.m. and it just, shuts off, not fully off, but just to the 50%. Or it turns off when there is, no activity present for 15 minutes, or you're doing the 1 hour before closing and 1 hour after or before opening type of deal. So it's on when it needs to be on and it's off when it needs to be off. Now, it also talks about exterior parking lighting, and make sure that, understand this is, for the exterior. Now, has anybody looked at a lighting fixture schedule on a set of plans, and they talk about parking lighting, and then they mention how tall the pole is. The reason why they're mentioning how tall the pole is because if it happens to be 24 feet or less, now all of a sudden you have to pay attention to this, where the controlled to automatically reduce by 50% when there's no activity for 15 minutes. And you can't have more than 1,500 watts that are controlled together. That's why the height of the pole makes an impact on how you look at it for energy. And I will tell you, I see plans that sometimes they bold that 24 or it's 20, whatever it is. They bold it to make sure that, you know, I don't have, or I'm going to comply with this. Time switch controls. So time switch controls are required. You have to have the capability of programming it for those 7 days, and you have to have different types of days, right? Is it during the week? Is it the weekend? That type of deal. You also have to incorporate a holiday schedule into all of it. And then have the capability that for the 10 hours that power is interrupted, that it can hold that programming for at least 10 hours. So here's an example of it on the plans. What I had was hours of operation, dusk to dawn, exterior lighting to be controlled by the library's control panel with photocell and timer. Now that note doesn't give me all the information I need. What it does tell me is it had the correct controls, but do those controls function the way that they need to? And they had a sequence of operation that said, hey, these controls are going to function like this. Good to go, which of course I didn't put it in there. So this is new in the 24. You must have lighting controls for your parking garage. They have to be on an occupancy sensor or a timer. They've got to reduce the lighting by 30%, a minimum of 30%, after 20 minutes of nobody being in that section. Now, that zone can only control up to 3,600 square feet unless you meet the criteria of the foot candle that the building code requires. Again, entrances and exits. It does allow for eye adaptation for it, right? So it's now saying that it can't be more than the 50% on that. And then here's the really fun one. So if you happen to have open garages, that opening, you now are going to apply daylight responsive controls to those openings. So it may be that your parking garage not only is dealing with this, but it also could be dealing with daylight responsive controls. So there are some exceptions to that, and some of that deals with where is it at? Is there a building next to it that's going to hinder any daylight from coming in, or there's not enough daylight in there? If there's some obstructions in the way, if you have a window to wall ratio, right? So it does give you some, I would say, common sense exceptions to that. All right, our interior lighting power densities, right? How much lighting can I put in our spaces? You've got two options. You can go with the building area method, or you can go with the space by space method. If we go with the building area method, basically what you're doing is not necessarily that the whole building is a library, but let's pretend the whole building is a library. You're going to utilize the number out of the table. This one is a 0.83. Let's say it's 1,000 square feet. You are allowed 830 watts. We'll pretend that Hope did math really well. That's how much lighting you get to use for your particular project. So in this one, it's not breaking that building down per se. But if you had a floor that was a library and then above it was going to be a courthouse, you wouldn't utilize the library lighting values for the courthouse. You would use the courthouse values for it. But if the entire building was a library, then you would use just the library on it. Oh, so here's an example. Here's a hospital. They're allowed out of the table a 0.96 lighting power density. It's a really small hospital. It's only 1,000 square feet. So when you multiply that, you get 960 watts. I pick 1,000 because that's a number Hope can do the math really quick standing up here. The second option is a space by space method. Now this is one that it's a little bit more intricate in how you do it. Maybe you have, like I said, you have a library. In that library, you have a reading area, you have restrooms, you have a break area, you have open offices, you have that part right there that Hope can't think of anything else that might be in a library. And so what you get to do is you get to take the values out of each part of it and do it that way instead of just saying, hey, carte blanche, it's a library, we're going to do this and be done. This gives you the opportunity that maybe instead of, the 0.83 that the library has, the 0.83 for a library might be there, but the reading area gets all the way up to a 0.98. So maybe you want to utilize the different values that you get out of the different spaces. So that's one of the benefits of going with the space by space method. Another benefit is if you use the space by space method, you get additional power lighting wattage for it. And so it's really dependent on the different areas. And so you get for our retail, if you are under like category 1, you get an additional 0.5, 2 is 0.5, 3 is 0.05, and 4 is 1.87 in addition. So the various areas come with that. Now, I don't have the section in here, and I know we're running short on time, but another thing to keep in mind is this section also goes and extends into additional lighting that goes for like art galleries or museums where they're showing displays, that they get some additional power wattage to it also. Lighting for plant growth. Well, this is where you get to make fun of Hope. So in this instance, what they're saying is because lighting for plants is, they utilize a different metric because the light that we need for humans is lumens, right? But the lighting for plants is that up there. And so what it is you have to ensure that the lighting has a photon efficiency of 1.6 MICRO. Thank you. I can't say that. That's my aluminum and spaghetti. Some people say, I don't know what they paschetti or, stuff like that. Mine is my blah. That per joule, that is a requirement. And so you'll see that a lot now. I don't know if anybody's been noticing any plant growth lighting that they're providing that information now. So let's talk about our exterior lighting power density, just like our interior lighting power density. Now, one of the things that you have for this is you can have CommCheck interior lighting compliance certificate that provides all that information for you. You also have this for exterior lighting, because it's the same thing. There's a requirement that you can only utilize so much power to light up the exterior. And so this one has a slightly different table. It's dependent on your zone, and they're not talking about climate zone here, they're talking about your lighting zone here. So if you were a residential area, you're going to follow zone 2. If you're a metropolitan area, you know, downtown Denver, you're going to follow the requirements for zone 4. And then when you go into the table, basically it says for zone 2, for parking lighting, you only get 0.5. I don't know what the real number is, but 0.5. So then you're going to multiply the 0.5 for all of your outdoor parking, and that's how much lighting you are permitted. Now, when you go into ComCheck, it has, you put all that information in for your project, it says, okay, you are permitted this much wattage. And then you say, great. And then you put in what you want to do, and then it lets you know, hey, you're better, or come back and try again, because this isn't going to work. So typically I get an exterior lighting compliance certificate, but if somebody wanted to do all the math, they absolutely could. All right. Dwelling units on the commercial side are required to have their own separate electrical meter. I can't tell you how wonderful this is. Anybody live in an apartment where the utility bill, no matter what the size of it, is split up amongst all of the apartments equally? Whether you're a single person who is only there 2 days a week compared to the teenage boy that has, or girl, has the lights on because they can't figure out how that light switch works, right? And they also have the TV on, the computer on, the console, the, you know, whatever, they're charging their 5 phones and all that fun stuff that is using all that. I used to live in an apartment where it was that way, and it used to drive me nuts because I'm like, I'm really good. And I know my neighbor because I knew my neighbor. I'm like, they're not as due diligent as I would like. And so it's really nice to know what you're doing, because it's hard for you to judge how energy efficient you are being if you don't get actual information, right? In our houses, when you get a utility bill, how many of you check to see, ooh, am I using more energy than I did last month? Yeah, me too. So if you don't have that information, you don't know whether or not you need to pay attention to what the heck is going on. Now I know it's my husband, he leaves all the lights on, so. All right, yes?
You have like electric utility meters. Is sub-metering acceptable to meet this, comply with this?
I'm sorry, what?
Sub-metering.
Yeah, as long as it's a separate meter for each unit, that is perfectly okay. What they want is they want for each unit to get accurate information of how much electrical energy they're utilizing. How you go about that, it doesn't necessarily specifically say. All right, elevators. How many of you knew elevators had energy requirements? So, elevators have a few things that they need to do. You have to ensure that the luminaires in the cab do not have less than 35 lumens per watt, and that the ventilation fans in the elevator without air conditioning systems are up to 0.33 watts of CFM as the max. And then my favorite is controls that de-energize the lighting and ventilation when it hasn't been active, the doors have been active for 15 minutes. So forever and a day, I've said that. How many of you have ever been to the Colorado Chapter's Ed Institute down, well, now in Loveland? And you know those elevators are glass elevators? At different times of the day, I sit there and I wait because I want to get a picture of it actually being de-energized. But obviously, as you know, everybody's going up and down those elevators, and I sleep at 2 o'clock in the morning. So I've never been able to get a picture of it, but I was in a hotel in Minnesota, and I walked in, checked in, I'm getting ready to go, and I was waiting for the elevator. It immediately dinged. The lights had been shut off, the ventilation had been shut off, and it started to kick in like 2 seconds after the door had opened. I'm like, oh, that's really cool. Duh, another time that Hope wished she had her phone out to take video of it. So again, people probably thought I was a lurcher or whatever you want, because I'm just sitting there in the chairs just waiting for it to not activate. The problem is it's right next to the Mayo Clinic, so those elevators are always being active. I finally figured out I'm just not going to get it there. But anyway, I digress. You also have requirements for escalators and moving walks. I don't know if you have many of these getting installed here. Elevators, you probably do. These, you probably don't as much. But there's a few things involved with it. Energy recovery for the escalators to kind of, collect things. This is the fun one. Automatic controlled receptacles. I used to work in an office that had these in this jurisdiction, and I'd be doing a plan review, and Hope is notorious for not saving her work. And I would get called up to go to the front counter to answer a question. I think they had it on 15 minutes. And so everything would shut down if you weren't sitting at your desk for 15 minutes. Hope redid plan review comments on many occasions. You would think with as many times that Hope had to redo her plan review after already doing it once, she would remember to start saving her stuff. But we had a permit tech that very intense sometimes, and somebody would come to the counter and they would just panic a little bit, and then they come back, you have to come up right now. Okay, no, you have to come up right now. It's really important. I'm like, okay. You go up there, and it probably wasn't as bad, but I got into the habit of I just have to go for it. It's all my fault. I'm the one who didn't save it. But anyway, so what they're asking is that you have to have 50% of your receptacles that are 15 and 20 amp in your enclosed office, conference rooms, break rooms, rooms that are going to do copy or printing, classrooms, individual work areas, including our lovely module office, right? I used to call it the fabric office. I had a fabric office as an inspector and plans examiner. I love those because I could stand up and talk to the zoning inspector that was the next little wall over. So you got to have it. It's got to be shown on the plans. Now, the function that it must do is it basically is going to shut it off after 20 minutes of nobody being there. It should also be on a time of day control. The controls have to be marked, obviously in accordance with the NEC, because the NEC is already dealing with that. They have to be uniformly distributed, meaning you can't have all of them here. They've got to be everywhere, which kind of the NEC already addresses too, but it's in here too. Now, the fun thing is, wherever you have a controlled receptacle, within 12 inches of it, you also have to have a non-controlled receptacle if you don't have a split, right? So basically, you can't have a controlled receptacle here and then say, I provided a non-controlled receptacle It's just 10 feet up there trying to push everyone to use the controlled receptacle. They're saying, if it's here, it's got to be right here. That's that kind of concept for it. And you can't use a plug-in for it. So here's a great example, right? Controlled, not controlled. Now there are some exceptions here. If it is something that has to be on 24 hours, something if it's not on or not, plugged in or whatever you want to say, that it could endanger the safety or security. The one thing that they have is those modular office workspaces. Instead of having it within 12 inches, they're saying 72 inches of the workspace because they're trying to take into account that, distances and all that fun stuff with it. Now, I don't know if you can see the picture really well. When you look at the picture, anything you see that should meet the exception? Soda machine? Fridge? What about coffee pot? Really? You think you stop me from getting my coffee that doesn't endanger the safety and security of others? You got to have fun with it. I have to say, I will tell you that this has tried to get into the code since at least the 2015 edition of the code. Because I had worked in a location that had these, and what happened is because everybody was losing all their work and there were so many issues with it that people were taking, because we didn't have the split. We had, I think, like maybe 3 receptacles in the area that were not controlled. So what they did is it went extension cord, power strip, extension cord, power strip to everyone in those instances. Just because we didn't have the criteria in here that said, hey, 50-50. And so we had one of those situations where we had the open office, but to get to the back where everybody was, it was a door. Our fire guys would walk in, they talked to the open part, they never once went through the door, and probably because they knew what the situation was, and if they saw it, then they would have to address it, right? In my head, that's why they never went past that door. Like I said, it kept trying to get in, and I fought it tooth and nail at the mic because I knew how it worked and what everybody's solution was that they were doing the daisy chain effect, to the point of where fire would come over and speak against it every single time. And I'd walk up to get in line and they're like, oh, no, Hope, start us off. So I always got to be at the front of the line talking about it because I'm speaking from experience in all of that. To the point of the proponent who has submitted this cycle after cycle after cycle said if I did not speak against it this go around, he would send me on a trip to Tahiti. I've never been to Tahiti because Tahiti's not worth my integrity. So I told here's the sad thing is, I told that story at the Ed Institute. His daughter was in my classroom. And I said that, and I'm like, well, it's not a big surprise. Her dad did it. That's how it goes. Anyway, so here's an example in an office of where they were showing those controlled receptacles. Now, one thing to keep in mind and is the additional efficiency criteria. And I bring this up because there is a lot that kind of revolves around it when we start talking about mechanical and lighting. You got to get 10 points, right? If you're, a new building, if you're a tenant space, you have to obtain 5 points in your project. For the most part, you're going to be doing additional things, more than one item, to get to those 10 points. Now, here are all the options. You'll notice number 1 deals with mechanical, number 2 deals with lighting, 3 is lighting, 4 kind of falls under its own little deal. Number 5, mechanical. 6 kind of falls under mechanical a little bit, service water heating. That doesn't. Energy monitoring, that falls into both mechanical and lighting provisions. Fault detection, when you're not required to install fault detection, but you do install fault detection, you get to take it. And then kitchen equipment, that doesn't do it. So, but you'll notice it's pretty heavily dominated with options for mechanical and lighting. So, first one is basically your heating and cooling equipment. You're going to demonstrate they're either 5% better than what's listed in the code for efficiency or 10% better. Please keep in mind when we're talking about the efficiencies of mechanical equipment, the federal minimum might be 80%. The best it can be is an 83% or an 82%. So not all equipment, actually most equipment, is not going to be able to hit the 5% or 10%. So just be, fully aware of this. And if you're the designer, make sure you provide the documentation saying this is the piece of equipment I'm going to do. The minimum is 80%, and this gets all the way up to 87. And the 87 is what we're going to do. Again, I'm not sure what 5 or 8, 10% of 80 is. So that's why those imaginary numbers work in the world of hope. The next one is your reduced lighting power density. So we just talked about lighting power and how much you get to use. If you choose this one, which is often the one that in the past where you would do one and done in the 18 and previous editions, they would choose this because the lighting industry has gotten so much better. It was really easy to achieve this. Now they're saying if you go with 10%, you're going to follow where you're 10% better, right? You're using 10% less of your lighting power that's allowed for you. Then you're going to obtain the points that are listed in the table. If you're able to reduce it by 15% or more, you get to take the value that's in that table, then you get to do an equation. That equation gives you a ridiculous amount of points because it is a huge improvement on the amount of energy efficiency that happens with it. All the values that you'll see in the table, the numbers that are in the table, were done through PNNL by climate zone and everything to say, like you get 5 points in theory, that's a 5% increase in energy efficiency. It's not exact, but that's kind of the concept that they were trying to equate it to. All right, so this one in theory could potentially be one and done. We have enhanced digital lighting controls. So you're going with you have daylight responsive controls. Now what you're going to do is make it even more advanced. A great example is there's this building department, I won't say where, I love going to because they have enhanced digital lighting controls that, turn the lights on, depending on the day, how much lighting's coming in and everything. So if you meet all of the criteria here, the big one is on the plans, having the sequence of operation that's going to outline it. The other one I really like is commissioning of functional lighting controls. That's listed in there. 408 already says you have to have those controls having the functional testing. But at least they made sure everybody understood you absolutely have to have it there. On-site renewable energy. So this is a new addition to the additional efficiency requirements. This is basically, you have two options on how you want to get there. you can demonstrate that you are providing or producing either 0.86 BTUs per hour per square foot or a 0.25 watts per square foot of the conditioned floor area of that building. The other one is that you're going to have not less than 2% of what the annual energy used within the building and this is for their mechanical and service water heating equipment and the lighting. The other one is also your renewable credit here, where the total minimum of the rating of an on-site renewable system exceeds what's in 406.5.1, then additional efficiency credits, you then get to utilize a wonderful equation. It's really down there, it's really small. I have yet to ever see anybody use this. I've actually yet to see anybody use this really at all on the commercial side. DOAS systems. Anybody seeing DOAS systems getting installed? A lot of the dedicated outdoor air systems meets the criteria that's listed in here, but they're not taking credit for it as an additional efficiency option because most people don't know that it's available for them with this. So this is one that, makes sense. Let's start getting the word out. You're already doing a DOAS system. Does it meet this? Do you need to make a small tweak to meet this information, this criteria? Might make sense. Reduced energy usage for service water heating. This is only an option that's available to the occupancies that are listed here. As you can see, those occupancies are water driven, right? Restaurants use a lot of water. Hotels definitely use a lot of water, because most people are like, I'm at a hotel, they have an infinite amount of water for them. And then what you're going to do is that you're going to demonstrate that 10% or more of the total building energy loads, when you do the calculation out of C407, that you're meeting that. Now, what you're going to do is if you're one of those ones and you're choosing this, you have to choose one of the three options here, whether it's recovered or renewable water heating. You have if you're using fossil fuel water heater, but it's really efficient, or you're going to use a heat pump water heater, and you would follow the criteria for that. Energy monitoring. I didn't put that in there, but there's a requirement now for energy monitoring depending on the size of the building. Most of the buildings that are being built up here aren't necessarily meeting that criteria, for the 21. But if they choose that they're going to go ahead and install an energy monitoring system, they're like, why wouldn't we give them the opportunity to take credit for going that step beyond? Fault detection and diagnostic system. This is, again, when you're not required to install it, but you do install it, then you can take credit for it as long as you meet all 6 of the criteria that's being listed there. Last but not least is the fact that if you have efficient kitchen equipment, now how this works is that you have to have at least one gas or electric fryer, and then all of your fryers. So it's not saying, so it says all of your fryers. And then it says all of your dishwashers, your steam cookers and ovens. Where it says at least one gas or electric fryer is what they're trying to say here is to meet this, you have to have a fryer, a dishwasher, steam cooker, and oven, right? That's how you qualify for this. It's not like, hey, I have this, I only have a fryer. You don't qualify for this credit. Make sense? I get questions on this all the time. So at that point, that's when all of this would kick into it. So here's the fun table. you can't really tell, I made pretty colors on it so that you could see things that were electrical and things that were considered to be mechanical driven, and then, you know, no colors for things that didn't fall into that. But if you are a Group B occupancy, and we're in 6B right here, this is saying, okay, depending on what you're doing, you'll notice for a B occupancy, you're going to do more than one, unless you meet 15% for your reduced lighting power density, then you might get there. For Group R and Group I occupancies, our big one is if you have recovered or renewable water heating, that gives you 15. Our Group E occupancies, you are not going to find a one and done. You will be doing multiple or really reduced lighting power density. Reduced lighting for Group M. If you utilize reduced lighting power as your option here, you can't go space by space method and do the additional lighting that you get. That's why Group M occupancies get so much, because they can't utilize that additional lighting for it. And then anything outside of the occupancies I just mentioned, this is the table that you would follow for that. That is it. Any questions?